series data would require this alignment. So the other problem is reconstruction. So this reconstruction can be a simple task such as denoising. When we talk about medical imaging, right, there are a lot of hardware components which would finally result in the image. So there will be a lot of noise that can be added when we're getting the final output. So denoising is a simple reconstruction problem where you want to eliminate the noise. And similarly, when you're talking about MRI or thermal data, you'll be capturing different views. And for a doctor, it might not be easier to interpret these multiple volume of data. So to make the visualization easier, many times we reconstruct this serial data into a volume data, 3D data. So in thermal images, you can assume it as 3D volume data. So this is a reconstruction problem. Apart from this, there are various applications like synthesizing the data. That is, can we create more data from the existing images? And can we model the treatment? And can we automatically generate the report with the natural language processing? So there are various tasks. So in order to bring an artificial intelligence product into healthcare, there are various steps that are required. The first one is the problem formulation itself. So what is the problem we are trying to solve? Is it a classification problem? So if it is a classification problem, what is the main hypothesis or objective of the study? Is it to validate the sensitivity of the technique, or is it to improve the specificity? So first, the step involves itself is problem formulation. So according to the problem, the next step is data collection, followed by data annotation and AI development. But these three tasks are not easy when we deal with medical imaging data. This is because often the data collection in medical imaging takes a lot of time, because in order to collect the data in a hospital, you need to take multiple approvals. You need to get ethics committee approval, you need to get scientific approval, which takes itself a lot of time. A simple scenario: when we were conducting a study in a hospital, we had to get this ethics committee approval and scientific committee approval. And the doctors for this scientific board meets once in 6 months. So we have to wait for 6 months to get the approval and then get their feedback and accordingly modify the protocol and then initiate the study. Even after initiation of the study, what we might expect is not large volume of data. The volume of data would be low because when we're talking about cancers and when we select only one clinical site, the number of walk-ins to the hospital for that cancer, right, is less than 10. So that means at most we can collect 300 or maybe 600 in a hospital site. So this makes it difficult if you want to collect large volume of data, because every subject we are collecting, we need to pay for hospitals, we need to pay for the patients, we need to take care of the insurance. So that there are multiple cost factors that are involved. So that is one of the reason why if you see any open source data set of medical imaging, we only get very small data sets. That is maybe a couple of hundreds like that. Whereas when we see the non-medical imaging data, we get like millions of data. So that is the main difference between non-medical imaging and the medical imaging. And the other important factor is velocity. As we discussed, we only get 10 subjects per day. So that means even to collect 10,000 images, we might have to wait more than a year to get that data. And since we are collecting this data at one particular site, maybe if you're collecting this data in Bangalore, the data is very biased to the population that are living in Bangalore. And the cancers or any kind of problem which you're trying to solve, the data which you're collecting is biased to the population around it. And when we want to make it a global model, you will see a new variety of data where algorithm might not work well. The other problem is imbalanced data. So the incidence of many of the medical diseases are very low. That is, if you're talking about breast cancer, the incidence would be like 4 in 1,000 or 18,000, depending on the country. So that means we have to screen 1,000 women in order to get 4 to 8 positive cases. This is on the screening perspective. So, so what we end up most of the times is a low variety and very small malignant data, very small abnormal data sets. So the algorithms, when we design, we have to take care of this imbalance as well as the variety. And the next step is data annotation. So for any problem, we need to know what is the ground truth. For some of the problems, it is pretty straightforward. Like if you're considering a X-ray image and you want to match it with radiologist decision, all you would be needing is contacting multiple radiologists, getting the final annotation from them, and then training a model with the corresponding labels. But even that is not the ultimate ground truth, because many of the many studies show that the radiologist performance or sensitivity specificity would be around 90 to 95%. Even this is like considering the radiologist is an expert. So in most scenarios, the ultimate ground truth is histopathological analysis of the samples. So we might have to collect the histopathology for the ground truth. And if not, then we have to have some parameters to take care of the subjectivity in the ground truth. So data annotation, we need to be clear whether the data annotation can be subjective or whether it is a standard ground truth. So this is one important factor for data annotation. The next is developing the AI model using the collected data. If you consider any kind of non-medical imaging problem, most scenarios, your task stops at AI development itself. And once you have AI development, you will have real world surveillance. But to bring AI product into market, there are three additional steps which we need to consider. One is a clinical study. That is, once you have developed the model, you have to prospectively evaluate. When you say prospectively, it means that you have developed a model, you close the model, and then you give it to a hospital. And then hospital will validate whether your solution is giving whatever metrics you have listed in your documentation. So once this prospective clinical study is done showing that indeed the AI model is working, the next step is to get the regulatory approvals. So this regulatory approvals could be CE if you want to market this in Europe, and this would be FDA if you want to market in US, and for India, DCGA approval would be sufficient. However, this itself, conducting a clinical study and getting regulatory approvals, because regulatory approvals take more than 6 months to 1 year, and this assuming that you have submitted the regulatory documents. But to create those documents, it again takes more than a year, and to conduct a clinical study, it takes much longer. So that is why when we see any kind of AI startups or AI products which you see, in order to get into market, it takes a lot of time for them. So once we get regulatory approval, the next one is clinical integration. That is giving it to the doctors and seeing where it fits in the workflow. That is one important factor. So here, two main parameters for better clinical adaptability is how interpretable or how explainable your AI model is. It is not simply sufficient to say given an X-ray image saying that the patient has COVID or not. It is not sufficient for the doctor to know whether it's yes or no. The doctor has to understand why this AI model is telling it is a positive. So the report or the predictions have to be interpretable as well as explainable for better clinical integration. And once you integrate, you have to monitor your AI model to see whether it is within the limits of the specified metrics. So with this, I will jump to Mirabai's thermolytics breast imaging system. So breast cancer is one of the leading cause of cancer deaths among women all over the world. If you see the statistics in 2018, 627,000 women lost their lives to this disease. Though in developed countries like United States, the survival rate is 80%. In India, it is only 50%. That is, every two women who are diagnosed with breast cancer, one woman is losing their lives to this disease. One of the main reason is late detection of cancer. That is, typically in India or developing or underdeveloped countries, we detect cancer in later stages such as stage 3, stage 4, where the survival rates are very low. Why is this happening? This is because one of the conventional imaging that is followed in Western world is X-ray mammography, ultrasound. Now, if you see these equipments or these imaging modalities, they have challenges when we try to implement in countries like India or any other developing country. First one is equipment cost. Mammography is very costly, and MRI is also very costly. And infrastructure, they require a dedicated room with a power supply. And for MRI machines, you need a room which is completely protected. Even for mammography, in order to seal the radiation, there are minimum requirements for the room. These machines are not portable, and you need high expertise in order to interpret the images. And another factor which we have seen in South Asian countries, why women don't go for mammography screening or breast imaging is that patients have to undress in front of a technician. And most scenarios, the technicians are male technicians. So so in a study conducted by Forbes et al., they realized that 70% of Asian women don't prefer screening for this reason. So along with this, X-ray mammography works only for women above 40 years because X-ray mammography relies on the density differences. For women below 40 years, the tissue itself is dense, so it would be hard to separate between what is a malignant tissue and what is a dense tissue. So it is not recommended for younger women or women with dense breast. And since it uses X-rays, there is a chance of getting cancer by with the repeated exposure to this radiation. So that is why in US and other countries, it is not recommended more than once in 2 to 3 years. So coming to ultrasound, it relies on the sound waves. And the challenge for using ultrasound in India is mostly that it can be used for fetal sex determination. Due to this, government has regulated its usage, and we can't directly go and do a rural screening camp with ultrasound without proper approvals. So this makes the usage of ultrasound in India difficult. And MRI, it is not portable, and it is only recommended for high-risk women because it raises a lot of false positives. So these three, though has been successful in Western world, they are even according to the World Health Organization, these are not suitable for countries like India. So clinical breast examination is often used in these countries, which has only 50% sensitivity. That is, it will miss half the cancers. And when we're talking about clinical breast examination, it is nothing but a person will uh, self-examine the breast, and um, they will try to see whether there are lumps or whether there are any hard regions in the breast region. So as you can expect, this is very subjective and can only detect once the tumor is fully grown. So that is one of the reasons for late detection of cancers in India. So what we are trying to do is, can we come up with a imaging modality which can address most of the issues what we have listed here. So we found that breast thermography is an imaging modality which captures the temperature values or infrared radiation emitted from the breast surface. So this infrared radiation, long infrared radiation, can be converted to get the temperature values. When there are cancer cells inside the body, they require more resources for their growth. So due to this, they employ more blood vessels. They employ the dormant blood vessels. There are a number of branches that form, and the vessels will get dilated. This process is called neoangiogenesis. So with this increased in activity of blood flow, we might expect to see more heat pattern. And it is also observed that the rate of blood flow that is goes inside the tumor region um, is lower compared to the rate at which it comes out. So due to this, we expect a heat pattern. We expect heat to be released due to this reaction. So this metabolic heat can be transferred to the surface through venous convection and tissue conduction. So with the advances in thermal cameras, we can detect minute temperatures up to zero point 0.02 degrees centigrade. So it might allow us to study the variations due to different abnormal conditions in the breast region. So what are the advantages of breast thermography? If you see, it is completely non-contact, it is non-invasive, it is radiation-free, it is portable, light, small, low-cost device. So you can carry it in a backpack and then do rural screening camps. It is privacy aware, um, which means that we since we are capturing the thermal image from very far, uh, we can we can keep this thermal camera or thermal device in a room, and the patient can go inside and we can completely operate the equipment from outside. And it can work with dense breast, and since, as we discussed, it is radiation free, that is there is no induced radiation or ionizing radiation that we're giving. It is only the radiation that is emitted from the body itself. It is completely safe and can be taken any number of times. What are the main challenges? So the main challenge is interpretation of breast thermal images. There are close to 400,000 color shades one has to look at in order to classify whether an image is positive or not. So it is taxing, it is subjective, and the high thermal patterns are due to benign conditions as well. And other thing is, since we are talking about the temperature values, there is no standardized representation for visual analysis. So if you're talking, so typically what it's being done is, once we get the temperature matrix, we use some color palettes. As you can see here, we are using a rainbow color palette. So we use rainbow color palette to convert these temperature values into the color images. That is, we simply map 25 degrees centigrade to black color, 39 degrees centigrade to white, and anything in between we linearly map it. Now, the problem is, depending on what color bar we choose, the heat pattern looks completely different. If you select, these both are belongs to the same image, and the temperature matrix which is behind it is the same thing. But if you select the limits as 25 and 39, that is mapping 39 to white region and 25 to black, we get an image like this. The same temperatures, when we map 28 to uh, black and 36 to white, we get an image like this. So on the left hand side, we can't see clearly heat pattern. On the right hand side, we can see a malignancy or abnormal heat pattern. So this makes it very subjective. And when we see in the literature, there are studies that say thermography is very good, and there are studies that say thermography is not good. Due to this, there is an equivocal recommendation for the usage of thermal imaging for breast cancer. So what we are trying to do is, can we remove this subjectivity? So how can we do that? Can we use artificial intelligence and then eliminate this subjectivity and convert this image into quantified parameters, which can help the radiologist in understanding the heat patterns and then giving a accurate conclusion. So in order to do that, it is not a simple problem because for any medical imaging, you need to ensure a different thing so that the output what we're giving is appropriate. So for this, what we have is whether the image is good or bad. So we have an image quality module, which basically filters out any kind of bad images or any kind of wrong images. So we have a deep learning module which tells whether the images are good or bad for the next steps. And since we're capturing the images from neck to abdomen, we need to identify what is the region of interest where we want to do the analysis, followed by where the abnormality is, and identifying some features, and then classifying it into whether it is a positive or negative. So these are various steps which are involved in any kind of automated breast thermal analysis. In this one, I would be briefly talking about region of interest segmentation. So these are the 5 thermal images which are captured for a patient. So we capture this multi-view because a single view is not sufficient to capture the entire breast. As you can see in frontal, we are not seeing the side portion. So due to this, we capture oblique and lateral views. So for this, we have 5 views. Now the task is to segment the breast region because that's where we are more interested in to find the cancers in the breast region. But this problem is not trivial because we are not seeing any hard boundaries or any strong edges we are seeing. So, and the other challenge is we need to segment this breast region in multiple views, not in a single view. And each view has a different orientation of the breast and different portion of the breast as well. So the problem is it's a multi-view segmentation problem. And there are no strict boundaries, unlike other object detection algorithms. And even when we compare the similarity between the segmentations done by one expert to the other, the inter-observer dissimilarity is only 91%. That is, there is a lot of subjectivity in the ground truth. There is no direct, um, there is no standard ground truths for this problem. So even an accurate model, in other words, right, even an accurate model would be only 91 to 92% accurate because there is a gap in the final ground truth itself. And other problem is when we started this problem, we only have 50 subjects, which is basically of low volume and low variety of data. Now, the question is, how do we apply machine learning for these medical images? right? So if it is some kind of tabular or structured data, we know, I mean, we can directly use different classifiers or a neural network or MLP. But images are unstructured data. So for that, there are two common techniques that are employed. One is traditional machine learning and other is deep learning. So in traditional machine learning, what we do is we convert this unstructured data into structured data. And then we apply the machine learning models to train and classify for a task. So the common ways of converting this unstructured to structured data is to extract some important parameters. This we can do from the domain knowledge, or this can be done using some statistical parameters like knowing what is the mean of the image, what is the median of the image, and what is the textual properties, that is second order moments, what are the second order moments, what are the first order moments, or knowing the domain knowledge, which means we know that if there is a lesion, there is a high color intensity lesion. So we can do some localization of this lesion, and then we can study the properties of this lesion. So malignant lesions tend to be irregular in shape. So we can find some irregularity parameters. We can see how intense this lesion is. We can study some shape parameters, and then we can classify whether it is a positive for malignancy or negative for malignancy. So now for the problem of this region of interest segmentation, we had to come up with some domain knowledge which can be helpful for us to identify the breast region. So what we thought was we can approximate the breast region as the region enclosed by four boundaries. One is the lower boundary, one is the upper boundary, a side boundary, and mid body boundary. And now the task is how can we estimate these each of the boundaries? To detect the lower boundary, what we have done was we went with a region-based detection technique. So as we said, this is a thermal image and we are not seeing any strong boundaries. If you are going with some edge-based techniques, what we might end up is a lot of disconnected edges. And that becomes a little bit a difficult task how to join these edges. So we directly went with the region-based techniques. So which means that we know the histogram of the entire body. And then we come up with some parameters using the training data set to estimate the threshold what we need to select for inframemory fold region. So once we find that particular region, we consider the upper boundary as the lower boundary of our breast region. And now to get the upper boundary, the same technique is employed, but instead we searched for these high temperature regions on the upper half of the image. And once we get that, this corresponds to the axillary region. And we can take the lower boundary of the axillary region as the upper boundary of the breast region. And however, this technique, we saw that it is not working well. Even in this image, it was able to find only on the left hand side, but it's not able to find on the right hand side. So we went with a heuristic. So for that, what we have done was we assumed that the height of the breast region is half the body width. With this assumption, now the task is to find what is the body width. So for that, we have used auto segmentation to get the foreground region. So auto segmentation basically, if there are multiple classes, it minimizes the interclass variance and maximizes the interclass variance and minimizes the intraclass variance. So it finds such threshold which can give this value as maximum. And once we get this foreground segmentation, we can find what is the body width, and we considered half the body width and estimated the upper boundary from the already detected lower boundary. And to get the side boundaries, we just used this ortho segmentation. After getting this foreground region, we just performed a simple edge detection algorithm and got the side boundaries. Now for the mid-body boundary, again, we came up with heuristic. Because the breast regions are symmetrical, it is fair to assume in the frontal view, the mid-body boundary is nothing but a line, is a segment that divides the right boundary and left boundary in 1:1 region because it is symmetrical. And the same is applicable when the patient is in lateral view. However, for oblique view, when we calculate using rotation geometry, we observe this for an oblique view of 45 degrees. This ratio is close to 1:2. So with these approximations from an image, we're able to get the mid-body boundary, the side boundaries, and upper boundary of the upper boundary of the breast region, and the lower boundary of breast region. Now we find a region that is enclosing all these four. And then we proposed a polygon-based segmentation so that we can display this to user. I will talk more details about why we are doing this polygon approximation. But as you can see from these four boundaries, we can able to approximate the breast region. So, and to present our result, accuracy is not a good metric for this problem, because in the entire image, only 20% might be the breast region, and remaining region is non-breast pixels. So even if the algorithm classifies everything as negative, we still end up getting 80% accuracy. This is because there is a lot of imbalance in the positive and negative pixels. So for this problem, we have employed dice index, which is nothing but intersection over union. So this can solve this imbalance issue and can tell us how similar two different structures are. So we tested this handcrafted traditional machine learning approach, and we found that the dice index was 80%. However, as you might have expected, there are a lot of heuristics. That is, a lot of assumptions when we made this segmentation algorithm. And when we tested on a real world scenario, that is from the data which is different from the training and testing, and is done by a different person altogether, the imaging, we were able to get only 70% dye similarity. This is because results are highly dependent on imaging protocol. That is, when we made this algorithm, we relied on the data that is at hand, and we come up with the heuristics. But it is very difficult to employ this in the field. That is, we can't expect the oblique view is always 45 degrees. It can be 50 degrees, it can be 52 degrees centigrade. So the segmentation might be off in these scenarios. So to avoid that, we used hybrid intelligence. This is for the initial purpose. So what we have done was, once we predict the region, we have displayed this segmentation to the user in a polygon format, and all the vertices can be adjusted. So the user can drag these vertices to adjust the region. So what it has helped us in is it saves a lot of time for the technician. So instead of doing this entire manual segmentation, maybe 30% of the time only they have to do this. And for doing this, it is also easier because they just need to drag some vertices. So we found that it can reduce the overall time for segmentation, and it can be an initial bootstrapping approach for the model deployment. So once we have set this model in the hospital, now we have 1,000 subjects data. And then we thought, can we use some kind of data-driven algorithms like a deep learning approach? So deep learning is a data-driven approach, and specifically for medical images, convolution neural networks is a class of deep learning specifically used for analysis of the images. So what CNN does is it eliminates the manual feature engineering, and it can learn the complex features with the help of different convolution layers in the network. So instead of relying on low-level features, it extracts high-level semantic features. So to implement a deep learning solution for this task, there are three main steps we have to follow. One is identifying what architecture we use and what would be our training data set and what is our loss function. So we have chosen VNet architecture. So VNet is an encoder-decoder architecture. So you have an image during encoder, we downsample the images and we extract some high-level semantic latent information. And we use this information and we upscale it to reconstruct the segmentation output. Each of the encoder and decoder are connected for better reconstruction. And you can also see residual skip connections even in the layers to reduce gradient vanishing or gradient explosion problem. So once we select this VNet architecture, now the task is about training. So the VNet architecture, the model itself has millions of parameters. However, the data what we have is only 1,000 subjects. The question is whether it is sufficient to train our deep learning architecture. What we have done is we have synthesized a lot of data by performing different augmentation. So we perform mainly 4 augmentations based on this problem. One is Gaussian noise addition. So you can treat Gaussian noise addition as the noise or the interference that happens during the imaging. It could be because of the dust particles, or it could be because of the room temperature. We might, or the equipment itself. We might see some kind of noise in the image. So to simulate this, we have used Gaussian noise and created a noise data set into our training. And we have done random cropping and resize. As you can expect, there are no standard guidelines for the imaging. A patient can capture from mouth till abdomen, and a patient can capture from neck to abdomen. So that is, different technicians can capture images differently. So in order to replicate, what we have done is random resize and crop, where we have randomly removed some top rows, side rows, and bottom rows, so that we get a different variations in the imaging. For this problem, so for this problem, since the problem is about segmentation, we are not so much interested in the heat pattern inside it. And as we talked, the incidence of cancers, there's a high imbalance between malignant and non-malignant subjects. So we expect our breast segmentation to work even in the malignant scenarios, even though we don't have large data set of malignant patients. So in order to create that, what we have done was we have randomly selected some regions in the breast region, and we have bumped the temperature values. So this will artificially create tumor regions. So this random region insertion is done so that we get equal number of malignant cases as well as normal cases. So the next modification we done was thermal sensitivity. So each camera has a different sensitivity. Some cameras can measure 0.02 degrees centigrade minor temperature variation. Some can measure only 0.1 degree centigrade variations. Since we want our algorithm to work for any kind of camera, so we have taken a high resolution camera and try to synthesize these different sensitivities from that high resolution camera. So that way our model would be invariant to the Gaussian noise. It is invariant to the technician protocols. It is invariant to whether it is a malignant heat pattern or not, and invariant to camera also. Along with this, to increase the data set, we have flipped the image. However, there is still another task that is left. As you can see here, in a frontal image, the model has to segment two regions. Whereas in oblique view, the model has to segment only one region, even though we can see the other portion of the breast region. The question is, how do we convey the model to only segment two breasts for frontal and one breast for oblique or lateral view, even though it can see the other breast as well. So what we have done was, to avoid this confusion, we only train our architecture by feeding the left breast images. And the problem for the deep learning model is it has to identify where is the left breast in the image. Even though it sees the right breast, we say we'll ignore. So the model can learn to detect right breast. And to get the right breast information, what we do is, when we flip the right breast becomes left breast. So the model can detect the left breast and we reflip it so that you can get the segmentation for the right breast. So that was the logic we employed. So a summary wise, a VNet architecture with 5 stages is employed. The model is only trained by feeding left views. And to get right breast segmentation, so what we have done was, we flipped the image, passed it to the model, and we got the segmentation output. And we flipped it back again to get the right breast segmentation. So to train the model, we have used a variant of Dice loss. So Dice loss, as I briefly discussed, it is it is minimally affected with the imbalance in the data set because it only compares what is detected. So we have taken dice instead of standard mean square error, all these things which could be affected by imbalance problem. And we introduced this new parameter which basically tells that even though the model is predicting some additional region outside the marked breast region, it is still fine because as long as the centroid remains same. This was done so that there is no strong upper boundary or anything, and there is no way to tell whether this segmentation, the blue top region, is correct or the aqua color boundary is correct. So due to this, we have added this constraint to allow both these scenarios. So these are the results which we have obtained for the segmentation of breast thermal images. So as you can see here, even though the images are too far, even though the images are not as per protocol, the green pixels shows the predicted segmentation, and the blue pixels show the manual segmentation, and aqua is the overlapped region. And as you can see, both the segmentations are very close, and human, when we do a visual interpretation, they're very accurate. And we compare the same thing with our traditional image processing approach. You can see it failed when for younger women where there is no inframammary fold. So we can see a shift in the breast region, and when the view itself is not 45 degrees, it is 55 degrees. That point of time also the segmentation failed, whereas the deep learning model was able to predict in both these scenarios. And when we measured dice similarity, it is 92%. This is actually greater than 91% inter-observer dice correlation, which shows that the proposed solution is almost performing similar to human expert. And we found that it is robust to image capture errors. Now, the next thing is in order to achieve these results, we can't get these results from the start, right? So we need to know at what point we got and is there a way we can improve this. So what we have done was we have out of the entire data what we have taken only small chunks of data. We have taken only 100 images and trained the model and computed the dice index. As expected, the dice index is only 0.55. And when we increased to 1000, it became 0.65, and 5000, it became to 0.8. And at 10,000, it became 0.92. So below this, the results were more or less comparable to even the traditional imaging processing approach. But when we slowly increase the data, the AUC has improved. However, it remained constant even we are improving the data set. So this can be seen for two reasons. One is that, as we have mentioned, there is a variation or subjectivity in the ground truth. Because there is no standard way of reporting the ground truth, it might, in this scenario, 100% dice index cannot be achieved because even with humans itself, there is a variation in the ground truth, and at most we are getting only 91 to 92% similarity. So that could be one reason. And other reason is that if you feed same kind of images without any variety of data, the model won't be learned. The model won't be learning anything. So those are the two takeaways from this experimentation. So as we have seen here, data is playing a crucial role, but getting data in medical imaging is difficult. So are there any ways we can solve this? So one way we have tried is data synthesis with generative adversarial networks. So generative adversarial networks were proposed like 5-6 years back, and it has seen very good results in synthesizing or predicting the actual data distribution. So think about this generative adversarial network problem of generating digits. So you have a generator and you have a discriminator. So generator takes a Gaussian noise and randomly generates some image. Now the discriminator job is to classify these images as non-digit images. But the generator task is to fool the discriminator. So this creates a min-max problem. And when we run for sufficient iterations, we will see both will be coming to an optimal point where you can see that the generator will be able to generate images that are as close as to the real images. So the same for brush thermal images. What we have done was we have taken Gaussian noise. We have a generator model which generated randomly some images. And for the discriminator, we said that whatever the image generated by generator is a non-brush thermal image. And whatever is generated by, whatever is actual brush thermal is the positive image. So we train the discriminator to accurately classify that whatever images generated as negative and the real images as real. And for training the generator parameters, we train such a way that the generator can fool the discriminator. With this minimax problem, after 150 epochs, when we give a random Gaussian noise, right, as you can see on the left-hand side, we were able to generate an image that is as close as to the real brush thermal image. And these are different variations of brush thermal images. So these images can be now used for manually segmenting the data and then getting more data for segmentation and retraining our models. So another way is active learning. So this involves once you deploy the model, you automatically refine your model, retrain your model, and then update the model for better results. So this is an active learning concept. That is, you will deploy the model, and you will have some error function which triggers whether the model have to be retrained or not. And once it retrains, it will redeploy into the production for real-time updation or real-time learning of the model. So that concludes my talk, and I would be happy if to take any questions.
Thank you, sir. Sir, as of now, there is no questions. Thank you, sir, for your yes, uh, well done speech. And I just wanted to thank you from on behalf of Bangalore Institute of Technology and from Electronics and Communication Research Center. I thank Mr. Shivateja Kakileti sir for spending his valuable time to provide knowledge to all the participants. So regarding this, raising an awareness about this medical images and the calculation, whatever you taught us today, is an important issue which requires dedication, commitment, and the passion. Maybe most importantly, public perception about the breast cancer has drastically changed because of the increase in awareness and the early detection. Thank you, sir, for explaining us about the really very important topic and the calculation of these kind of medical images, and it is need for this generation study.
I think there is one question from.
Yes, sir. Please, thank you, sir. I'll just read out the question. The details of OOF. Please tell the details of OOF. How to use deep learning.
Okay, so the question about whether. Yeah,
Deep learning.
right. So that's a good question. So for this problem of breast thermal images, so what has happened is here we have defined what is a good or bad in three phases. So the technician hasn't captured the image properly in the sense that what we have seen is that sometimes they captured the face image also, which is not so relevant for our analysis. And what it creates is that the amount of breast region which we see in the image, the size reduces, right? So it is important to notify the technician that they have to adjust the camera so that most of the focus is on the breast region, and the regions which are not so important, that is abdomen or the face or the neck region, should not be more than 25% in the image. So to do that, we have used the same segmentation. So you can see that given an image, now the algorithm is able to predict where is the breast region. So now once you know the breast region, you know what is the height of the breast region from the top and what is the height of the breast region from the bottom and from the sides. So sides is also important because what we have observed is that sometimes technician when they're capturing the image, we might see that half portion is cut because they didn't adjust the camera properly and it is not in the field of view. So we use this segmentation, what we have briefly went through, and we have calculated what is the area and what is its position. Depending on that, we have classified whether this image is taken properly or not. So the second way of classifying whether the image is bad or not is whether the images are focused or not. So for that, we have a deep learning technique where we have created unfocused data set and a focused data set, and we have trained a simple mobile net architecture to classify whether it is a focused image or an unfocused image. And another common problem which we see in this good bad classifier is auto tagging. So what has happened? What is one of the main concern when the technicians are capturing these images is that they are labeling these images. Now, if they say that this image is left oblique. However, this image is right oblique. So if they say it's a left oblique or give misinformation, the results what we generate will also be wrong. So to avoid this, we have a view classifier, which we call it as auto tagging, which again we have manually coded all these 5 views. We have created a label data set, and we have trained a ResNet architecture to predict what view it is given this image. So these three we were using to tell whether an image that is uploaded by technician is good for processing or bad for processing. I hope it is clear, Mr. Gupta.
I think so. It is clear, sir. We have one more question, sir. What is the role of VLSI architecture in AI?
I think definitely any kind of deep learning solutions, we there are two things. We require a lot of GPUs, and the other thing is once we want to run this on the mobile platforms, so there the models we want there we want to run even on the smaller architectures. So now there is a lot of research that is going on how we can optimize the existing architectures in order to run these AI models with a small scale architectures because you can't expect a GPU to be on with everyone to run these inferences. We want it to be running on edge processors, and we want to run it on simple mobile devices, all these services. So definitely there is a huge scope in this.
I think so, sir. Whatever the answer you gave, it holds good for the VLSI design technology, which is used for breast imaging also, right, sir?
Right.
Thank you so much, sir, for your patience and your support towards our FDP program, sir.
Thank you.
So now I request all the other participants to join us at 11:30 for the next session, which is from Antara Roy Chaudhary, madam. So we'll meet at 11:30 a.m. Thank you. Now we'll have a short break.
Plot the different graphs with the data, and we'll see what kind of meaningful information we can get it. Okay, remember these two stages will come before you actually start working with the machine learning model building. Machine learning model building comes when you do the training, testing, data split, and all those stuff. Before that, we will see in the ADA or the exploratory data analysis, we will see how the data looks. Yesterday we did it, but we did not officially say the term as such. We did some statistical analysis with the function describe and all, if you remember. We'll do something else also today. Followed by we will do data visualization. Yesterday I did not do that at all. I'll do the data visualization and we'll do some kind of plotting, so scatter plot, box plot, and I'll show you how by looking at the graphical data, what are the meaningful information we can infer and how we can reshape the data or whatever it is. Okay, now followed by, yeah, so that's it, and followed by we'll do the ML model with the logistic regression. Without wasting much time, let me directly now go to code. So is the agenda of today how we are going to work with it, is it clear for everyone? Any question? Anything you want to ask me? Anything you want to change? Anything extra you want me to do? Okay, so let me just go to the EDA. Okay, so all of you, I hope all of you would have got this particular file EDA. Let me just zoom it a little bit more so it is visible. I hope it is visible. If the font is not visible to you, please let me know. Okay, so okay, so I asked you to please open this particular file of exploratory data analysis. Not visible. Okay, so someone is telling not visible. So let me zoom it. So now is it visible? Is it visible now? The other people can also say.
Yes, ma'am, it is visible, ma'am.
Okay, so some people told it's visible, it is clear. Yes, okay, fine, done. Then I'll move ahead. Okay, so with this exploratory data analysis, what is that we want to do? We want to do Vanish is telling better. So, so I'll just do one thing. I'll just do it once again, one more, because if I zoom it too much, no, so you won't be able to see the entire screen. So now, okay, fine, done. Fine then. Okay, so this is the area. So with area, what is that we want to do? You want to understand the data set and what is its shape. Yesterday we did it with the shape command. Followed by, we will see that what are the data type of the columns, and we'll check for the missing values and the summary of the data set, and followed by group by. These things mostly we did today, yesterday's session. I'll just quickly finish with this and see that what are the extra things we can do, and followed by I'll go to data visualization that we have not done. I'm just doing the ADA because that is the first part that has to be done. Now, so coming to that. So first thing what we have to do, we have to import the dependencies. So as we have done yesterday, I'll show you some 3-4 steps, followed by I'll give you time to execute it. Okay, please don't execute it right now so that you do not miss the explanation. So first thing is we are going to import 1 minute. Yeah, I'm going to, let me just close all the things so that it is easy for you. Okay. Just closed everything. So first section is my importing the dependencies. So what are the things we're importing? As we did yesterday, we imported the NumPy library and is imported with the name NP. NumPy library was used for the data processing, and then we used pandas, and we imported is at PD. So this is going to be useful for your data frame processing. Followed by, there is one more thing we are importing that we did not do yesterday. We are importing sklearn.preprocessing. From sklearn.preprocessing, we are importing something called label encoder. Okay, label encoder. Now, why we are importing it and why we need it, we'll see it in due course. Okay, remember this, we have imported something called label encoder. Okay, so this is your importing the library. Let me just finish it execution of this. We've imported the library. Now we'll do the data collection. So I hope everyone would have uploaded the data set. So we have to load the data set. So for that, the data is there in the CSV format. This is the data, right? Breast cancer initial data. I hope all of you have the data set. So this data set is there in a CSV format. To load or to read a CSV file, the command is pandas.pd dot read CSV. So that is what we have done, pd dot read CSV, and we have loaded the breast cancer data set in our environment. So let me execute it. So right now that CSV, from the CSV data set, we have got a data frame. So this breast cancer data is the data frame on which I'm going to do the further machine learning and commands. Now, coming to the area section, as of now, we are done loading the data. Now, coming to the exploratory data analysis. So, initial commands I show you very fast because this things yesterday we did. First one, if you want to look at the data, so we can print the 5 rows with the head command. So let me see how the data is there now. Okay, so this is what we have to see. So can you see how the data set is? So data set, the first column is called ID. And there is some values is put here. Maybe that is a patient identifier of a particular hospital. Some ID is put for me, followed by the second column, which is called the diagnosis. And I hope this one you can understand. This is a major column, which is my output as such, or the analysis as such, diagnosis. So this will have 2 values. One is M, another is B. So let me show you how the B is coming. Let me put a tail command, this one. Let me execute the tail command here. So if I execute the tail command, I think you will be able to get B. Yeah. So remember, this diagnosis column will have either M or B. M means that tumor is a malignant one, and the B means the tumor is a benign one. Okay. So this is how you can. So right now I have this is how your data will look. So identifier, diagnosis, and apart from this, you have all the features to work with. So you can scroll it here and there. So I'm just scrolling it right side. So radius mean, texture mean, perimeter mean, area mean, and all those things are data. There is a lot of columns are there. It's a big data set. A lot of columns are there regarding the tumor. Okay, apart from first two columns, all the things are about the feature of the tumor. Okay, so this is what you should see by the execution of the head and tail command. Now, so if you want to know what is the size of the data, we can execute the command shape. So let me execute this one. Yes, so I can see it's a data set of 32 columns, whereas 30 columns are the tumor features. One column is the ID. Another column is the actual prediction diagnosis, whether it's a benign one or the malignant one. And how many rows or how many patients data is there in that particular data set? It is 569. So we have 569 patients there. So now if you want to know that what are the columns are there and what is the data type of that column, so then we have to execute the info command. If you execute the info command, you will see that from 0th to 31st, because there are 32 columns, how many columns are, what are the columns I have, and what is the data type. That is what is a major thing that you should see here. So first one, ID is an integer type, and second one is an object. I mean, that is what is your categorical variable, the diagnosis, which is not a numeric one, it's a categorical variable. I hope all of you remember this diagnosis column will have two values, either it is M or B, malignant or the benign one. Okay, so and you can see here all the data, I mean all texture mean and whatever you have, everything is a floating type data. Only the integer is ID and the diagnosis is a categorical variable. Yes, I hope this much is clear. So now once you look at this particular data, I hope you understand I have to do something about this two initial columns. Okay, what are these two columns? ID, correct? So why I'm telling something I have to do about ID? Because I want to predict on the tumor features whether it's a benign one or it's a malignant one. Do you need patient identifier or ID for this? Of course, no. You don't need ID at all. So in that case, this ID, if I keep it in my data set, it will give you wrong results. If I use this ID column for the machine learning prediction model as well, it is going to give me the wrong result. So what is that I have to do? If you see any kind of data which is not necessary for modeling, first thing that you have to do, you have to drop that column. Okay, so this is a pre-processing data, pre-processing we are doing. So see the data and remove whichever is not needed. So here what we have done for that, we are dropping the column that is ID. So breast cancer data, what is this breast cancer data? I hope all of you remember breast cancer data is a data frame, correct? On which we are executing the command head, tell, info and all those stuff. From that, I'm going to drop a particular column. Yesterday also we have executed this command drop. And which column I want to drop? I want to drop the column ID. Okay, and why we are given here access equal to 1? Yesterday I told that one. If you want to delete a column, then access will be equal to 1. If you want to delete a row, then access is going to be 0. And in place equal to true, it says that modify the original data set. I mean, the original data set is breast cancer data. There only you delete it. You don't create a copy of it. You modify the original data set only, and from this original data set, this is breast cancer data on which you're executing the drop command, and there only you delete it off. Okay, so right now I have this ID command deleted. So if you want to see that, okay, let me just execute once again now. Let me create one more see. So let me execute the print command here, or the head command. Let me give it here. Breast cancer data. So let me just show it with the head command. Let me see that whether this ID got removed or not. So you can execute a particular code cell with this one, or else you can press Shift Enter. So once again, what happened? Did I execute this command? Just let me check it out. I think I have not executed. Yeah, so now it's fine. So yeah, so now if you can see here, the ID command got removed. Yes, so I have the data set which starts with the diagnosis, which is a categorical variable, followed by all the features of the data. Okay, so I request everyone, if you do not have any doubt, please finish up to this particular step. We're dropping this ID column and again give a head command given now, so that you can see the data set and see that whether the ID column has been removed or not. I request please everyone start coding. Any doubts? I'm opening my chat section. Please message it. That should I stop or should I anything you want me to do? I mean, these things, it should be easy to do because a lot of things yesterday I have explained. I'm just doing it again so that you're very confident about this data pre-processing stuff, because that is very, very essential. Okay. So someone has, can anyone please share the link of the project? Yes, I'll share. I have shared the link of the project. Everyone is getting access to the code. Please let me know. Yes, fine. Okay. So please open the file EDA, exploratory data analysis, and start the modification. Don't modify the original file. Please make a copy in your local disk. Sorry, local Google Drive. Let me know whether you're understanding or should I stop or repeat something. So as of now, what we did, we imported the required library, and we have seen how the data looks. And followed by, we have seen that what is the data field, we don't require it at all. So we are dropping that particular column. That's it. As of now, we did this one. So please message done once you are done with this steps execution. So I'll go ahead further. Rick, done. Okay. Ajay Abu said done. I'll wait for 1 or 2 minutes more, 1 minute more for the other people to finish. I request everyone to do it faster, also be responsive so that I can move fast also. Anyone else who wants me to wait or who is done already? If you want me to wait also, you can just please message that wait. Otherwise, I'll assume that it's done and I'll move. Kusuma, you have opened it in Python error. You have opened it in Google Colab, right? Yeah, execution depends on network speed. Yeah, correct. So is it getting executed? Yeah, so another person has messaged us it's done. Okay, so Ajay replied that he got an error while in the removing portion, but when I started again from beginning, the error was not there. Yeah, I think that the people, you are getting some error because you would have missed some step. You have seen that while I was executing initially, I got some error. Initially, I saw that the ID column was not removed. Then I executed it again. Maybe you have forgotten to execute some step. Just check it one by one. From if you are not getting the things, you just refresh it. I mean, again you go back and this 1 second only it will take to execute the steps again. You restart. Maybe you are forgetting to do something. A particular step you have not executed, so that the latest step it is giving you error. because we are all executing in the same environment. So ID should be in column. So once again, let me just solve this doubt. ID, ma'am, ID should be in column. ID is in the column. Initially, it will be there. I have shown, I'll just go to my screen again. Initially, I think all of you should have got the ID if you have used the same data set that I have given. Initially, no, it's a classification also. Yeah. So in the EDA, this is what a file I was executing. So yeah, initially when you have executed the head command, the ID was there. After that, I have removed it. So now ID will not be there. If you, but before, once you load the data set, it should be there. Okay. So now let me move forward. I hope this much is done for everyone. Okay. So right now we have, okay. So this is where I have, up to this I'm done with. So I have removed the unnecessary column, that is ID, and I have again executed the command head and checked that yes, my ID column got removed. So unnecessary column I don't have. Now, what about this diagnosis column? I know there's a categorical variable which is having the two values. One is M and another is B. So what we have to do with it? So remember, once you have a categorical variable, no, it is difficult to predict in that textual format, MB, like that. Okay, it is better to encode it with a numerical value. Remember, once you have a categorical value, say malignant, benign, or if you're predicting a weather of a day, it can be the value as say hot, cold, or medium. So don't work with those categorical values. You encode those values as a numerical one, say 0, 1, 2, whatever levels you want to give. So for that encoding, we are going to use the library function that you have encoded at the beginning, that is label encoder. Okay, in the beginning we have included this particular library for us, that is label encoder. So what we are going to do with this particular library now, let me go down, and here down, yeah. So you should start execution with this particular step where we are this column, a categorical column. We are changing the categorical column. Okay. So now come here. We have changed it here. Yeah, down. Okay. So I'll just show you this step first, maybe. Okay. Okay. Let me just go ahead and do it one by one. So remember whatever I was telling. So this categorical column will be changed here with the label encoder here. This is a code for changing. Okay. But before that, there are some other basic steps. Just let me execute it once. The first one, we have to check that whether do you have missing values or not. Yesterday with this one is null.sum. Let me execute it. It will show you that per column whether you have any missing value or not. So as of now, it is showing you everything 0, means the data set is clean and clear. You don't have any missing value. If you have any missing value, in that case, you are supposed to replace, either you can delete that row which has a missing value, or else replace the missing value with a mean or median. So right now, this particular data set, as you can see, it does not have any missing value for this one. Now, if you want to know the statistical information, what is the statistical information? Yesterday you have seen with the describe command, correct? You have executed the describe command and it will show you the statistical information of the mean, max, and all those stuff, correct? So mean, max, and all those stuff is shown. Now, by the way, yesterday also we have seen this information, but nothing much we did with it. So just let me tell you what you are going to infer out of this statistical information. So just let me have a look at it. What are the value you're getting? The minimum one, maximum one, then the average or mean, then this 25th percentile, 50th percentile, 75th percentile, and all those stuff. And this 50th percentile is nothing but your median. Okay, so this is the mean or average one. I hope my highlighting is clear to you. This is a mean or average one. And this 50%, 50th quartile, this is nothing but your median one. Okay, so remember one thing, once you see a data, I'm repeating, once you see a particular column, if you see the mean is larger than the median, I'm repeating, if you see the mean is larger than the median. Can you see here the situation is mean is larger than the median. This means the data is right skewed or right tailed. This will be more applicable to you, more understandable to you once I do the data visualization. Just remember it after this. Okay, so remember it. The first, when you see this mean is more than the median, in that case the data is right skewed one, and there's a chance of it will have some outliers. We will come to it, just give me some time. So as of now, this is the situation of the data, and I have noticed that here the mean is larger than the median, and it is true for most of the columns, not only radius mean. If you see that in the texture mean column as well, the mean is larger than the median. Can you see it's 19, here it is 18, here it is also it is 91, and it is 6. So most of the column, if you see here, the mean is larger than the median. It means the data is right tailed or right skewed. It will be more clear when I do the visualization. Okay, so this is what I told you, the mean and median. Just see it how close they are each other. So if the mean is more, then I'm going to understand it's a right skewed one. Now, so and the next thing, yesterday whatever we have done, we have to check for the class imbalance issue. So for that, we want to see this diagnosis column. In that, we are executing the command value count. Yesterday also we did. Let's see it how what it gives. It will give you the how many M you have and how many B you have. So it is telling you, okay, by the way, sorry. Yeah, correct. No, fine, no problem. So it is showing you that how many B or how many benign values you have. I have the benign values of 357 and I have the malignant values of 212. So can you see there is not too much difference in the values. Yesterday we said about the class imbalance issues. These are first things you should check for any data set. If you see that M is say 20 and the benign is 357, then you know that yeah, I have in the original data is very much biased, so which will not give me the clear-cut accuracy or the clear-cut prediction in this data is not fit for further processing. So here we know where we see that yes, it is not very much disproportionate, so I can go ahead and work with this method. So this data has the benign tumor data 357 and malignant tumor data of 212, 212. So this is almost the proper mix. So I can go ahead and check for the further modeling. Okay, so as of now, this much we are done with it. And now whichever I was talking before, that label encoding. Okay, so this is a new step. Yesterday, whichever we have not done. So let me say it again. What we want to do. Right now, my data has a categorical variable M and B, that is my diagnosis column. Instead of writing as M and B, I want to encode it as a numerical one, say 0 and 1. Okay, so for that, what you have to do, you have to use a library function label encoder. Okay, so first thing, I'm taking a reference of the label encoder, the label encode equal to label encoder. Okay, so now right now this label encode is my reference to the label encoder. Okay, now what I have to do, I have to do the encoding for which column? I have to do the label encoding for the column diagnosis. Correct. So we are doing that breast cancer data and we are going to that particular column diagnosis, and on that column we are applying the encode function and with the fit transform. We want that particular column to be changed and transformed with the encoding. Okay, and whatever is a new and this labels, so and that is getting stored as a column called labels. Okay, so this labels will have, someone is messaging me in the chat section something. Okay, let me just finish with this discussion and just wait. If you have some doubt, just 2 minutes, I'll get back. Let me just finish this step and then the other people can start execution. Okay, so this one, so yeah, so this up to this we have, I told you that this step will encode the column diagnosis and it will give you a column of 0 and 1s. Okay, that is there in my labels. Now what I want the column diagnosis, which has the M and B, to be dropped. And the same column, the labels, which is the encoded value of 0 and 1, corresponding to the diagnosis 1, should be there. So what I have to do, I have to add a column. Let me add the column name as target. target will be equal to labels. So what I'm doing in the breast cancer data, I'm adding a new column and I'm giving that column name as target, which will have the encoded value of 0 and 1. And 0 and 1 is a corresponding value of your diagnosis column. Okay, so right now I have a target column. So what I have to do, the original column diagnosis I have to drop, because that encoding I'm already done. So to drop that column diagnosis, what I have done here breast cancer data dot drop. Which particular column I'm dropping? I'm dropping the column diagnosis. Why axis equal to 1? Because before I have told that axis equal to 1 means you're dropping a column, and in place equal to true because you want to modify the original data frame. You don't want to make a copy of it. Okay, so now, so if I execute, let me execute this code here. So it is executed. So remember before, what was my data? If I have my head, I have executed here. Before, see how the data will change here. Before, this is your data. Diagnosis column was there. Then it started with radius, mean, and all this stuff. Now, if I have deleted the column diagnosis and I have added a new column called target. If you execute this one, and now if I print the head command, print it with the head command, what will you see? Can you see the diagnosis column is no more there? The first column diagnosis is not more there. That is changed. And let me scroll down here, right side. All of you should scroll down to the right hand side, and you should be able to get a column called target. Yeah, so can you see you have a column called target, which is all ones right now. I mean, it is a 1 or 0 depending on it's a malignant or the benign one. Yes, can you see this one? So this is the encoding, and so if you want to check the class imbalance situation, it's the same thing only. It will give you, instead of M and B, it will give you as 0 and 1. So if you can see that you have benign value of 357 and the malignant value of 212. I mean, the 0 is encoded as a benign ones, B, and that for the malignant you have replaced it with the value 1. So up to this, I'd request everyone to finish. I'll repeat the step what we have done. So I think before I asked you to do where have we stopped? Yeah, so I think we have stopped it here. Then I told you to check for the missing values with the isnal.sum, followed by you have checked with the describe command, you have checked the statistical analysis of the data, and I have said that's the right skewed data because the mean is more than the median. Followed by you have checked for the class imbalance problem with the command value command, and we have seen that in this column we have categorical column, we have a proper mix. Followed by we said we don't want to work with this string or the object kind of column or categorical column. Let me change it with a numerical one. So for that we have used a label encoder, and where the benign values are encoded with 0 and the malignant ones is encoded with 1. And after that we have printed the data with the head command. We have removed the original command diagnosis, and the label, after the label encoding, the command is my target, which command, sorry, column is my target. So you can see if you print it with the head command, you will no more see the diagnosis column beginning. It will not start with I'm scrolling left, so it is not starting with the column diagnosis at all. At the end we have the column called target. So up to this we are done with it. So as of now, which pre-processing steps we are done? Just let me say that what you should do once you download a data set. Once you download the data set, please import the proper library. Then import the data set in the CSV format. Then from the CSV format, you create the data set, data frame with a pandas dot or pd dot read CSV. Okay, followed by you should see the data, visualize the data, see the data. So for that you can use head command, info command, describe command, and see that what are the columns you have which is not necessary. Drop the columns which are not going to be necessary for the analysis purpose. Followed by you see you have any column which is not numerical. Okay, so you do the encoding for it. Okay, so as of now we are done up to this. Any data you get, first things up to this. So let me now go to the chat section and check out the status. Let me go down. Sorry, 1 second. Let me go down. Madam, I got an error in removing portion, but yeah, that's fine. ID should be, think. 1 second. After small break, when I tried to run remove ID step, so it will not be there. No, sir. You have removed the ID once. So now what you have done, you have changed the original data set only. That's what I showed, that there is a parameter called in place equal to true. So once you have the in place equal to true, means the original data set is getting modified. So after that, if there is no more ID column in that particular data set, if you want to try to again remove that ID, how you're going to get it? I hope that answers the question. If you want to again repeat that step, please start from beginning and load the original data, which will have the ID column. After removing, that ID column is no more there. So does it? Okay, so it answered the question. Start at count. So start at count, why? Can you share, Rama Kusma, can you just see that what is the issue with the count one? Count means you were, which count you are doing, the group by count? Or I'd ask again, you also that to restart it. What is the error it is giving for the group by count? I think the same thing is happening. You restart from beginning. You upload. You just remove the data set. I mean, what I'm suggesting is, you please go to this files. Okay, remove this data. First of all, you remove this data, and then I'm not doing this step. You do it. Remove this data and go to this edit and clear all output. Whoever is getting confused here in the execution, please do this way. You please remove this data set. Go to edit and click on this clear all outputs, and you restart the execution. You again reload and start from the beginning. If there is, because all the steps are like input of a step, output of a step is input for the next steps. So if one step is missed or not executed properly, it will be a problem. So please remove everything, click on the output and start. That's all I can suggest. I would have, it's an offline workshop, I could have gone there and debugged it, but since it's an online one, difficult for me to debug as such. That's why I'm sharing the code so that you can do it. That's it. Yeah, so let me just, yeah, so anyone, yeah, so as of now, we have removed. So yeah, so this much is done. Okay, this is the last step. You finish with this one also. So it's the last step. Okay. So as of now, we have encoded it, and my benign one is replaced with 0, and the malignant one is replaced with 1. And followed by what we did, we have done a group by mean. On which group by I have given? Group by on the target column. That is my benign or malignant, or 0 or 1. So let me see what information I can get it here. Let me execute this one. Okay, so it is giving you, yesterday also we did group by, right? So it will group by mean, it will give for both the groups. 0 is my benign group and 1 is my malignant group. So what is it? You can see that the benign tumors, the 0 is with 0, it's having the average radius of 12.14 something. Whereas the malignant tumors are having the radius of 17.46. So can you see here, not only this one, if you can see with all the other values also, the texture mean, perimeter mean, for everything, if you see all the other values of the tumor, can you see the malignant, for the malignant tumors, the values are in general larger than the values of the benign ones. Can you see that? So that's what we can comment out when you once a person has a larger tumor, when the size is, the tumor is very large, there is a more probability that it's a cancerous one. Okay, so that's what you can predict, I think, clearly from this data analysis. Yeah, so this is where your exploratory data analysis will finish with a basics of processing, where you really remove the unnecessary columns, did some encoding, and see that all the data to do some analysis and some information you have got it. So this is where we are finishing with exploratory data analysis. This is the first step, followed by we'll be continuing with data visualization. So I'd request everyone to finish up to this. I'll wait for 1 minute more, and then I'll go to the next file, that is my data visualization, where this will be the input. Okay, all these steps are there, followed by you are going to do some visualization, some graphs we will plot and see that how it looks and what is the information we can get out of it. Okay, so yeah, so now let me again go to the chat section, everyone. So yeah. Okay, so someone, yeah, so Ramba Kusuma said it's done. I'll wait for one last minute for all the other people. So only 1 or 2 people are responsive as such, that who are replying that it's done or not done. Yeah, Ajay Babu. The other people, people are stuck, or because I can see there are almost, if I remove the hosts also, it is almost 40 participants are there. So yeah, wait for the last minute and then I'll go to the next one. Okay, so Keshav said wait for 1 minute, ma'am. Okay, fine, Keshav, I'll wait. So please let me know, Keshav, when it's done. I'll wait. No problem. Let everyone finish. Once Keshav, if it is done, you please message, huh? Anyone not getting the output, please restart. Remove the data set, again upload, and restart from beginning. Done. Okay, very good. So let me start. I'm assuming it is done for other people also. So with the same data, let me start. All of you can open the second file. That is the exploratory data, not the EDA, we are done with it. Then go to the visualization one. There is visualization file is also shared with you. Okay, so let me open the file data visualization. Okay, so I think this is a file all of you are getting. So I'd request all of you to do the same thing again. Please connect it to the environment if it is not connected. For me, it's connected. If it is not if it is not connected to the Colab environment, please connect it here. Okay, please click on here. You should be able to get say connect symbol kind of a thing. Please connect it. Followed by go to this files, and it will not be uploaded for you. Please upload the same file, that is breast cancer initial data. Okay, I request everyone to please do it. Please upload the file breast connection data. Okay, so after you are done with it, so first thing, as I have said, that once you have a data, first thing you should upload the data to your environment, and followed by you should do the data pre-processing or the EDA, explorative data analysis. So here, these things are, I'm not showing you the code anymore. It is importing the dependencies and the data collection is there. So for the importing the, so I have, it is coded with a section. So first section is my importing the dependencies. So if you see, if I just want enlarge this section, so here all the other library will be there, same only. only once you want to do any kind of visualization. For the visualization, two things are imported extra. One is matplotlib function, matplotlib.pyplot. This is for plotting, and also seaborn library, which is imported as SNS. Okay, so PLT is a short form of matplot.pyplot, and for the seaborn we have used it at SNS. So this is used for plotting, this matplot library for plotting in Python. And on top, a seaborn is a library function which is done on top of matplotlib, which is a specialized one for the statistical kind of a plotting, statistical plotting, I should say. Okay, so once you have this, please import the dependencies quickly. For the data collection, you don't have to do anything because it's the same coding only. I'm not explaining. Please, if you want to check it out, what it is the same coding. Please enlarge it. Otherwise, just execute it. Okay, just execute it so that the data collection is done. Okay, once it is done, you know it is done now. So you can see the green symbol, it means it is done, followed by EDA. Whatever steps we are done, there are 22 steps we have executed just now. No need for any explanation more. Please execute it just like this. You execute it, it should be done. If you have imported the file properly, no need to change anything. It should be done. If you want to click on it, you can see it, everything is done, and you can check the output of all the cells. So it is actually, I'll suggest to better to code it in this way. What you can do once you are coding, so instead of coding only with the code text, you can insert it a section. So you can go to insert, and you can insert something called as a section header cell. Okay, so now if you code, so all the things will be under that particular section. So your code can have a section for the exploited data analysis, your code can have a section for the visualization, your code can have a section for the modeling, another section for the prediction. Okay, so that you can compile it in one shot. Okay, so up to this we are done. So I think everyone could finish this much. Please finish this much. I'll wait for 1 minute. Up to EDA, finish it everything. I mean, you don't have to expand and go. Please don't execute it one by one. It will take time. Just execute it in one shot and go down here up to the section where it will start with the data visualization. And initially it will be all closed, like this 22 cells hidden, you should be able to see. And please click on the small triangle symbol so that you can expand it. And from here, I'll start explaining line by line how to visualize the data, and what is the you can infer out of it, and how you can modify it, and all the stuff. What is the importance of data visualization? Everything I'll explain. So please finish it up to the EDA. It should take not more than 1 minute, I feel. So I'll just see the people if it is done. Please let me know once it is done, and I can start. Then I can start with the data visualization one. One person has messaged as done. I'll wait for 1 minute more. Everyone, please upload the file. Wait for 1 more minute. If anyone wants me to wait, please let me know. Wait, then I'll wait. Is there anyone who wants me to wait, or else I'll move? Okay, some other person also, Ajay, told that's done. So I'm assuming it is done for the other people. If anyone wants me to wait, please ping me. Okay, fine. So now, yeah, the Keshav was wrote is done. Good. Now, okay, so now start with the data visualization. So in the EDA, what we have seen there are two classes. If you remember, we had what we did in the EDA, we created a column called target, correct? And the target column will have the two values 0 and 1, correct? And what we have seen that how many there was, I guess, some 315 or something like that benign tumor values were there, and something 200 some values of malignant tumor values were there, correct? Now if you want to see that this class imbalance or how many values were there, instead of seeing it as a value, we better understand when we plot a graph with it. So what we have done, we have taken SNS. SNS is the short form of your CBONG. CBONG library you have imported with SNS. So SNS dot count plot. I mean, count the values and plot it. Okay, and which you want to count the values. You want to count the values on the target column, and which is my data set. The data set is my breast cancer data. Okay, this is a data set. Now let me execute it and show what it is giving you. Yes, so I think all of you should be, don't execute, let me show you and then you can execute, that's better. Okay, so yeah, so you should be able to get this kind of graph. So can you see this target, this x-axis, we have the target, and in the y-axis we have the count. So right now we know 0 or the benign value, I have larger, higher number of benign tumor data I have rather than the malignant tumor data. And you can see that how much difference is there. Yes, so this how with the visualization you can understand in 1 minute rather than looking at the values. Okay, there is one very simple plot we have done, counting plot, followed by distribution plot. It is called a pair plot. We'll come to this and what it looks, pair plots, pair plot, scatter plot, everything is there. So right now what I want to know that what are my columns are there, correct? So you had something, what are your columns that you can execute the info command, or with the Python, I want to print what are my columns, and we'll see that why I'm just doing it and what I'm going to do with it. So right now what I'm doing, I'm just iterating in my breast cancer data. This is a simple Python for loop. I hope all of you have the basic familiarity with the Python language. So what I'm doing, this is my data set, correct? This is my breast cancer data. On that, I'm looping with the for loop and I'm printing the column names, correct? But let me check if I executed what it gives me. Can you see right now it is printing all the columns which starts with radius mean, texture mean, perimeter mean, and all those stuff. And it should finish with my last variable. That is what we want to predict. That is my target column. Yes, so this what is my all the column names. Now followed by what I want to do, I want to do a distribution plot. What do I mean by a distribution plot? For every column, I want to see what is a distribution. What do I mean by what is a distribution? Let me show you the Kaggle dataset. Once this is a breast cancer data set in the Kaggle. Okay, by the way, I have downloaded this data set only and given it to you. If you want to download from Kaggle, you can go to this data set, breast cancer data set. Okay, let me go down, and this data set will, once you try to download it from Kaggle, it will show you for every data parameter, I mean, say radius mean, texture mean, and all those stuff. It will give you a distribution plot. Can you see? It will give you some kind of distribution plot, correct? Where you can understand the how the data. Can you see?
Window, icon.
Someone has unmuted. I request all the participants to please mute it. Yeah, so I think you can see the radius mean and all the things, distribution plots are there. And here also you can see the data is right. So if you want to get this kind of distribution in your coding, what you are supposed to do, right now I know these are my columns, correct? I have got all my columns. Now for each one of these columns, I want to do the distribution plot. So that's what we have done here. So for column in breast cancer data, for the distribution plot, the command is SNS.displot. Displot is for distribution plot. Okay, SNS is for my CBONG library. On the CBONG library, I am executing the function called displot, where in the x-axis I am plotting the columns, whichever column I have, and the distribution will be loaded from the data set, that is my breast cancer data. Okay, so this function, this will take a little bit of time because there are 30 around columns I have. For all the columns, it will iterate. So this for loop will iterate over all the columns and give me 30 plots in that case, depending on how many ever columns you have, how many ever features you have. So you'll get the distribution plot for everything. Let me execute this command and I'll show you that if after executing what kind of curve we get and what is that I'm going to infer out of it. Okay, let me go down. It is executing actually. So it is taking some time, as I have said you. So see, you can see a lot of graphs are getting plotted. So let me go now. Let me scroll up. Okay. So let me go up. As I said, it will give you around 30 plots, correct? We have 30 columns, 30 features, I should say. For every feature, it will, for a feature or every independent variable, I'm plotting the graph and trying to check how is the data? What is the distribution of the data? There's a lot of graphs are there. Let me go to the beginning. Okay, let me go up faster. Okay, let me go up 1 minute. Yeah. This is the starting one, that is radius mean. So if you see here, this is a distribution plot for radius mean, followed by we have it for cell detection mean and all those stuff. Now, by now also, if you see that plot, I think you can understand the data is right skewed. Right skewed means, can you see the data is right side? You have a tail, correct? So data is right skewed. It is true for the radius mean. It is for the detection. Can you see there's some here? Yes, it is true for all the other features most likely. Can you see the data is right skewed? And this is what I have inferred before also. If you remember in the EDA, you have given a command called describe. And I have said, if the mean is larger than median, in that case, I can see the data is right skewed and vice versa. So the same thing I'm verifying with the visualization also. Correct. So I can see that how this is data is going fine. But in the right hand side, I have a tail, something like this. So once you see this kind of data, which is right skewed or left skewed, whatever it is, okay, and you have some data point which is isolated. Can you see there is for everything, for all the graphs, you are seeing some data point which is a little bit isolated, I can feel, correct? This is nothing but outlier. By the way, what is outlier? Suppose I'm plotting, or I have a column of age. Okay, one parameter is the age of all the patients, and you have the values from same say 20 to 70, something like that. And all of a sudden you see when you plot the age like this, and you see there is a value of 200 or there is a value of 0. What do you understand out of it? That data might have come from the wrong typing, or that data is not a valid data. So this data, whichever you see, which is isolated one in the topmost left hand side or the topmost right hand side, that is most likely which is my outlier, which we should not consider for the model building. Correct? No, if you have a age is a parameter, and if you see the age is 200, should I map it for the model building? No, I know that maybe the age was 20, and by mistake the person was typed it, instead of typing as 20, he has added one more 0. So those are the things you should remove. So that is the first step, one more, that is called outlier detection and outlier removal. Okay. So firstly, you should see that what are my columns I have. Check out the distribution with this, either with this command, but with the visualization, you can understand. So with the visualization, you can see if we have an outlier or not. If you have an outlier, means yes, I have to remove it, or else you have to replace it with some other value. So we'll come to it what to be done. So I think you can understand that right now I'm plotting for all the things, and there is a chance that there is some kind of outlier I have. So I'd request everyone to finish up to this. Please plot it up to this, and whether you are getting this right skewed data. Can you see this? Always I have some outlier there. Some of the data is finishing here, but you have something here and here. So please finish everyone up to this. Then I'll go to the next plotting. I request everyone to finish up to the plotting. Madam, do we have to do this outlier remover for yesterday database? Yes. So yes, sir. If you see that there is some kind of data, the outlier is there. Okay. It's looking like histogram. Yes, it's a histogram. It's a distribution image, correct? So yes, if you see some kind of outliers are there, then outliers are either it has to be removed or it has to be replaced with the mean or median value. We'll come to it. For any kind of data set, these are the steps you are supposed to do. This EDA and visualization and removing the missing values, removing the unnecessary columns, encoding the categorical columns is necessary for whatever data set you get. Okay, so I'll move. So is it done up to this? This distribution plot is done for everyone. Can I move? Okay, done. One person has told done. Yeah, done. Okay, so 2% finishing means I'm assuming the others have done. If anyone wants me to wait, please message here. Otherwise, I'm moving. Done. Good. Okay. So now, so yeah, so distribution plot, and we have the idea that there may be an outlier, and we have to do something with it. This one you remember, followed by what we can do. Okay, so I'll show you the outlier removal also if you want. Okay, let me go ahead one by one because that code is a bit down. So I'll show you how to do what to do with the outlier. As of now, you understand with this, I have an idea that there is an outlier maybe there, and that I'll verify with the box plot also. I'll show you that one. So before that, we can do something with the pair plotting also. So pair plotting means we are going to do some kind of a, we are going to pairwise the features I'm going to plot, or else you can do it with a scatter plot also. So what I want to do, scatter plot of the first two columns. So what is my first two columns if I have to see? I mean, you can check out which columns you want, and you can plot the columns and you can check it out. I mean, if I go up, what are the columns I have? I have the column, first two columns means one column is a radius mean, second one is a texture mean. So you can plot any column. So right now here I have extracted my first column. iLog will give you go to that particular index and colon comma 0, because don't nothing before column is because row for all the rows go to the 0th column. For all the second column is for all the rows go to the first column. So here I'm extracting the first and the second column, and then let me print here. In the second, I'm printing the first and the second column. So what are the first and second column I got? The first column I have got at my radius mean, and the second column I have got as my texture mean. And what you can do a scatter plot printing. So for the scatter plot, I have to use you don't need any Seabong library. You can do it directly with the matplotlib that is imported with a PLT. You can do it with a plt.scatter. So if I execute this one, so you can see the distribution of your different parameters. Okay, so it is a plotting of your, I mean, what is the relation, whether they're related or not, how is the correlation between the different parameters. So you can check it out for whichever parameters, whichever features there are 30 features, whichever features you feel that with the most important features, you can check between with the scatter plot. Now, the most important that I was talking about it, that is my outlier detection. So outlier detection, we had the idea with your distribution plot, correct? That there may be an outlier. So that you can validate again with something called as a box plot. Okay, so let me execute the box plot command. What is that we have done? For column in breast cancer data, I mean, what is my column? I think you remember column is an array of all the column names. Okay, so I'm going to iterate over every column and I'm going to print it. And what kind of printing I want to do? I want to print a box plot. Okay, that you can see breast cancer data dot box plot and execute it on each and every column. So it will iterate over, and instead of getting distribution plot 30, I'm going to get now the box plot. The box plot, how it is going to show me, let me execute, and there only will get a clear-cut understanding of outlier. It will take some time because it will have 30. Yeah, so now if you see. So, okay, by the way, what is a box plot? I just go to this PPT and show you once, and then I'll show you how to understand this one. Okay, let me go to the slideshow. So once you have a box plot, so you will have this kind of situation. Okay, first middle line will be your 50th percentile, or the median. Okay, 50th percentile. Left hand side you will have the upper one or lower, whatever it is. One more line will be there for the Q1, that is my 25th percentile. Another will be the 75th percentile, that is Q3. Okay, Q2 is my 50th. Now there will be two more extreme lines in the left hand and the right hand side, or top or down, whatever it is. This is called the lower extreme value. What is this value? This is Q1 minus 1.5 IQR. What is this IQR? IQR is called interquartile range. What is this interquartile range? I think you can understand this is nothing but my Q3 minus Q1. This is nothing but my Q3 minus Q1. Correct? Q3 is my 75th percentile. Q1 is my 25th percentile. So this interquartile range is nothing but Q3 minus Q1. So what is this line? This point is my Q1 minus 1.5 IQR, and this one is Q3 plus, sorry, Q3 minus 1.5 IQR. Okay, so this is my lower extreme. This is just a mathematical formula, no big deal is there. Okay, this is my lower extreme and this is my upper extreme. Okay, now once this is the box plot will give you. Now once you do the box plotting for each and every column, if you see some values which is outside this range, this is the lower extreme, this is upper extreme. If you see some data value which is there beyond this range, those are my possible outliers which has to be removed. Am I clear? You will see the box plot, you will see this lower extreme and the upper extreme lines. If you see some values are there which is outside these two lines, I know that these are my outliers which has to be removed or replaced with the mean value or median value. Now, so I'm almost, it is 3 minutes are there. Okay, let me just, I'll just take 1 minute and then you can just execute it. One minute, 1 second. Yeah, so now if you execute this box plot command, can you see for this verse, can you, this is the box I have, and there are so many outliers up. So if you can see all the things, so you will see there is a lot of outliers. Can you see? You can execute and check it out. There is a lot of okay, let me scroll up. Sorry, let me go to the first one, that is my radius mean and the perimeter mean. 1 minute. Go up. Yeah, so if you go for each and every column, whichever column you want, you can check it out, and that is a possible outlier. So you can understand there is a data which is wrongly added or whatever it is. So I know that there is an outlier, correct? So can you see that from the box plot, you should be able to identify, yes, clearly I have some outlier. Now, once you know that you have outlier, in that case, in generally, there is a thumb rule. If there is a lot of outlier is there, then you can replace it with a median. I'm highlighting this line. If you have a lot of outlier, then you can replace it with a median values. Median value, that is my 50th percentile. If there is a less outlier, then you can replace with a mean value. As a thumb rule, we say that. Or else you may decide to remove the outliers. Okay, I'll just show you how to remove the outlier. This correlation matrix, I'll show it after the lunch break. I'll just show you that this outlier removal. So this portion remove, remember I'm not showing it right now. Correlation matrix, I'll show it after the lunch break. So once you know that there is an outlier, you can replace it or else you can remove it. I'm just showing you how to remove it. Okay, for the removal, what I have to do, I have to know which are the data set which is outside the boundary. So I have to calculate my Q3, Q1 and Q3. So Q1 and Q3 is your 25th percentile and the 75th percentile. Followed by, you have to get your IQR or your interquartile range. Executing this command, and I'm printing my IQR for each and every column. Now what I have to do, this is a code, you can check it out afterwards also. This is where we are checking if the value is less than the lower extreme or the value is more than upper extreme. This is my outlier, right? If the value is less than lower extreme or the value is more than upper extreme, then what we are supposed to do, you are going to remove that one from the original breast cancer data. I'm going to remove all the values which is less than the lower extreme or more than the lower extreme. Let me execute it. You should be able to see the output. So if I'm removing the outlier, now if you see, now I have 569 rows. Can you see right now I have 569 rows? And if you remember initially, I think you had some 700 rows. Okay, so let me go up in the data ADA. ADA, somewhere I would have done this shape command. Yeah, in the shape, no, I think I have gone down only. You can go up in the particular section. I think there was some 7, just show it once. It was there. It was there. I think there was some 712 rows were there. Okay. So right now, so this is where I'm ending. You can start execution, and once you are done, you can proceed for the lunch break. I think it is already 1 o'clock. So please finish it up to this. So where I'm finishing now, we have done the distribution plot, and we have said that there is a very important step that we have to take it out. That is my outlier detection and outlier removal or outlier replacement. So we have seen that we can particularly see with the box plot. We have plotted the box plot. Then I have showed you how to detect the outlier, which is less than the Q1 minus 1.5 IQR or Q3 minus 1.5 IQR. And we have checked that which are the data which is outside those, and we have removed that. So this one we are done with it. So I think one person told it's done. So up to this, if it is done, anyone with any doubt? We are still at the data pre-processing state. So afternoon, I'll be showing you the pair plot, and followed by I'll analyze this data with the machine learning model, that is my logistic regression, and followed by I'll do the analysis with the neural network. No doubt. Okay. So if it's fine, then I request, I think we can proceed for, so the host can guide. Okay, so thank you. Thank you for the input.
Thank you, ma'am. So the afternoon session will start at 2 o'clock.
Done. Thank you.
Thank you, ma'am. Thank you.
Good afternoon, everyone. Welcome to the session 2 of day 2.
Good afternoon, sir. So can we start now?
Yes, madam.
Okay, so good afternoon to everyone. So in our last session, we have we started discussion on the breast cancer data. For a brief recap, we started with the EDA, that is exploratory data analysis, and we have seen that how to go through the data with different commands and how to remove the unnecessary columns. Followed by, we have seen that how we can have an idea that is an outlier kind of thing. Followed by, we proceeded with the data visualization, and I have shown you how to look at the distribution plot, followed by the scatter plot, and last we are doing the box plot. And I have shown you box plot is very much useful when you want to check out that if you have any kind of outline something which is not part of the valid data, that we should remove it before we actually start the machine learning model or deep learning model or artificial intelligence, whatever it is. That must be removed, or that should be replaced with the median or mean values depending on what is the situation. So up to this we are done, and I have shown you once we seen that there is a outlier, how to remove it, and we have done it here, outlier remover. So this is what we stopped, correct? So from there I'm continuing. So this data visualization, only one command was I have not done, that is this heat map, or this command is not done, correlation matrix. Okay, so this is the only thing which is not done. So I'll just explain this one. So by the way, before continuing with, anyone have any doubts in previous session, whatever we have done, anything you want me to repeat, anything we did not do? Okay, if there is nothing, then I'll just continue. So, so what we want to do here we want to plot the correlation matrix. So what do I mean by the correlation matrix? So here it will plot the correlation between all the different attributes. What do I mean by this? Let me execute and show this so that it is clear to you. Let me execute this one. I think it is not connected for me. 1 minute, it is still connecting. For you people also, if it has got disconnected, kindly connect it. Now it's connected. So it is blocked. Now I want to plot it. So I'll just show the how it is getting plotted and then I'll explain the command. It's taking some time to execute. 1 second, it will come. Okay, so this is output. Let me explain now what we want. So if you want, you can execute this command. It will take only 1 minute to execute, and so that you can see it from you, because it is quite small in the font. So I request participants, you can execute this 2 commands. This is the only thing pending in the data visualization, that creating the correlation matrix and then constructing the heat map or the correlation matrix for out of it. So this you can execute these 2 commands and see it in your screen rather than looking at here. It's a bit small here. So what we are doing here, I'll just try to zoom it also for your convenience. So here, this is a plot. I'll go down a little bit. Okay. Okay. So here, this is the plot. I think it is better in this way. You can see. So the plots are. So if you see here, we have a perimeter mean, area mean, smoothness mean, and all. And down we have the same columns. If you go down, why it is coming with ID, I think, just give me 1 second time. I'll just re-execute all the commands. Give me 1 minute, huh? It is coming with ID means it is not the, it got disconnected, it is removed. Just give me 1 second. If you also check it out, if it is coming with ID means ID, I hope all of you remember that ID column, we removed it. So whatever output I got, that is not the correct one. So let me execute it again once. 1 minute only it will take for me, not much time. So better you execute the EDA, whatever is there, totally you execute it in one shot. So this data visualization, other things you do not have to execute. You can directly go to the particular area where we have this section called this box plot and all these things are done. The correlation matrix. Now you will see this correlation matrix. Go there and again try to plot it. Okay, let me see now if I'm getting it properly or not. Yeah, now it's fine. See, so that's what I keep on telling you. If you're not getting the proper output, maybe somewhere some mistakes would have happened. Please restart. Okay. So yeah, so now the ID column, which was not unnecessary, that got removed. So here we have the radius mean. And if you see the down also, so what we have done in that y-axis also, we are plotting all the columns, okay, or whatever 30 columns we have, all the columns are plotted here. And in the down, if you see the x-axis, that is also starting with the all the columns. Okay, so basically all the columns are plotted against all the columns, and the correlation is marked with different correlation values. The values either it is 1.0 or so whatever it is, 0.03 or 1.0. So maximum value is 1.0. I think you can see it here. So if it is higher the correlation, it is plotted with a dark blue color. Lower the correlation, it is plotted with the lesser dark color. If there is no correlation, it is 0. Okay, so by this, okay, by the way, if you look at all the diagonals here, can you look at all the diagonals here? So you will see everything is 1. Okay, so basically it is radius is plotted against radius only. If you see here, because it is like radius is plotted against radius. Down also you will have something called the radius. All of you, I request everyone to see it in their own screen. Okay, so radius mean is plotted against, I'll go up again. Yeah, again it is plotted with a radius mean only, so the correlation is going to be 1. So always the diagonal values will be 1. Okay, now all the other values will indicate that range of correlation. Okay, now by the way, how we are plotting it? First here we have calculated the correlation, all these values, say 0.3, 0.2, it will calculate all the correlation. Now while plotting, you are initializing the plt.figure. Connected is getting disconnected for me. Okay, so we are plt.figure. This plt was a reference to our matplotlib library. Okay, and you are taking the size as 2020. You can change the size of the plotting area as well. Now you're plotting this heat map, sns.heatmap. SNS is my reference to the Seabong library. Okay, both the library we are using, matplotlib and Seabong. Seabong.heatmap. So what you want to plot? I want to plot the correlation matrix. C bar equal to true, that is my color bar. I want to plot with the colors. Now which color we want? We want the color, this is you can write, mention it as blue also. I want to do it with a blue color, and yeah, here it is mentioned as C map equal to blues. So I want to plot it with the different shades of blue. All the values should be, all the boxes should be annotated. So annotation equal to true. Format equal to 0.1f means I want to plot 1 decimal value. So you can see here all the values are written with a point decimal. So it is 0.1f means I want it to be only 1 decimal value should be written here. Annotation equal to true means it will be plotted here. And which color shading you want? I want it to be color mapped according to the shades of blue. Okay, and you can this was where we are saving the picture with a correlation heat map. So here, so this is how to plot it. I guess all of you would have got this output, is simple one only. Now what is that we are supposed to understand from here? What is that you can understand here? If you see the column between this radius mean and see this two. Okay, so radius mean will come at 1. That's fine. See this two here, I have 1 1, and here also I have one more 1 is there, correct? So now one second. So here we have 1 1. You can see here, this is also 1 1. We have 1 more 1 we have, correct? So what we can do here, so this to 1 means these two are very high correlation. So let me go down here. So what is this to value? So these two values are with reference to, let me go down. These two values are with reference to my perimeter mean and the area mean. So I know now this radius mean is very much highly correlated with perimeter mean and the area mean. Okay. So in your data set, if you see there are multiple columns, multi-collinearity we say, if there are multiple columns which are highly correlated to each other, in that case, if you keep all those columns, you're not going to get any extra information. Because one means if you increase radius means the other one is directly proportional to each other. That is a 1. If it is a -1, if you see any value as -1, that means that they are indirectly proportional to each other. If one is increasing, another one is decreasing. If you see a factor of 0.3, it means if radius mean is increasing, the another one will increase by 0.3. 3.3 multiplied by 0.3. So how they are proportional to each other? Or minus is proportional or indirectly proportional. Okay, reverse. Now, if any between value, see that between them. If one increases, what will happen to them? So now, if there are two parameters which is directly related to each other, then they do not give me any other new information. Correct. So it is better to, if there are multiple attributes are there which are directly correlated to each other, it is better to remove the all others apart from one. Okay, because if you keep more features, it will not give you any other new information. So remember, once you see that That is called feature elimination. This step is called feature elimination. Once you see there are more features which are directly correlated to each other, you may not keep everything. Okay, so that's what you should understand out of this data visualization. Okay, so that is the end of the data visualization, where you can see the data clearly, visualize the different kind of plot. You can understand what is the relation between different attribute, where are the outliers, how to remove the outliers. All the portions we have covered it. Now let me quickly move to the machine learning model, followed by the neural network or deep learning model. Okay, so now you can open the file breast cancer classification using machine learning. All of you, please, I'll wait for all of you. Please open the file. If you have any doubt in the data visualization, you can ask. Now the breast cancer data, we will be using a little bit different data set, I'll tell you. So breast cancer data, we'll be classifying it with two ways. One is a machine learning model, that is logistic regression, that is my classification. Another, we are going to use a deep learning model. We are going to take help of Keras and TensorFlow, and we'll see that is accuracy increasing, decreasing, or what is happening on the same data. So should I stop or can I continue? Okay, there is no more doubt. Some continue. Yeah, okay, done. So let me okay. So please open this breast cancer classification code. Let me explain quickly, because here initially this one I'll explain a little bit fast only, I should say, because this is the with the classification with the logistic regression, and logistic regression yesterday we are done, correct? So I'll just do this so that you can relate it to the neural network that I'm going to do next. Okay, so quickly I'll execute, just see it and you can do it with it. Okay, so first we are going to import all the dependencies. All these dependencies are already, I have shown it to you, nothing new. The trained test, split, accuracy score, logistic regression, everything all of you know. So just execute it. So okay, it is not connected for me, so it is taking some time. You can keep doing it along with the discussion, because these things are already shown to you. I have shown it to you. Yeah, so it's connected now. So dependencies are imported. So let me see, do I have the file here? Okay, by the way, I'm not going to load the file here. Okay, by the way, just listen to me for 1 minute. Yeah, so see, either you can, there are two ways. Either you can download the dataset from Kaggle. Okay, that's what I did last time. That okay, now download the dataset from Kaggle and you can import it. That's what I wish I said, right? Go to these files and right click on this and go to upload, correct? Or else in the library sklearn, okay, in the library sklearn, there are some standard datasets available. You can directly use that also. Okay, so in the library sklearn datasets, okay, you are using the sklearn datasets. So in there, the breast cancer dataset is already available. You can use that also. Otherwise, you can download it also. Anything is fine. Okay, so right now let me show it to you in this way. So here I have imported the datasets from sklearn. Okay, now in that dataset sklearn, in that particular dataset, we have a data set called breast cancer. So what we are going to do, we are going to load it. So if you see here, I'm just highlighting this particular line, breast cancer data set equal to sklearn dot dataset. So from the data set of sklearn, you load which one I want to load. I want to load the breast cancer data. So let me execute it. Okay, so right now this breast cancer data set is loaded for me. Okay, but can I use this directly for the processing? No. All of us, we know what we have to do. The CSV files or comma separate files, first we have to convert it as a pandas data frame so that I can process it, correct? So for that, we have the remaining steps. So first, initially, let me see that how is the file. Okay, so let me check it out. This breast cancer data I have got. So let me print it and see that what is the format of the file, how this file looks. So let me print this data. Okay, so I hope all of you know a little bit of Python directory. So is there anyone make screen big? Okay, fine, I'll do that. So now is it visible? Is it visible? Yes, okay, fine. If it is not visible at any point in time, feel free to stop, no problem. Okay, so if you print it, so what is it I'm getting? So this is my data, and I think all of you know this particular notation in Python. This particular notation, the curly braces says that the data is in the form of a dictionary. All of you try to remember that what is a dictionary. The dictionary in Python is a key value pair. I think all of us we know that, right? That in Python we'll have different data types. It can be the list or tuple or dictionary. So dictionary, if anything is there in this, by the way, anyone wants me to repeat that what is a dictionary in Python? For anyone, should I repeat that what is a dictionary in Python? Okay, fine. So here the data is in dictionary format. So if I see that I'll just let me see one screen. 1 second, someone is messaging. Just give me 1 second. Let someone plus screen. Big screen. So is it not visible? The other participant can also reply that. Should I zoom it more? Hello?
I have to little zoom in, man. It's not visible.
Okay. 1 second. I'll just try to see if I can do directly something here. I'll zoom it here. If I zoom, no, it entire code. So now is it fine? Or should I zoom more?
Yes, it's visible.
Okay. Blurred, maybe network issue. Okay, so is it coming blurred for someone? Now is it fine? Vanishri madam is telling it's fine. It is blurred. So I'll reconnect. If it is coming blurred, so everyone should say it is coming. So see, the network issue can be in both the directions. So if many people are telling it's blurred, then I should reconnect. I should try to reconnect. One person has stored blurred. For anyone else, is it coming blurred? Please reply. Is it clear or blurred? It's visible. Vanishri madam is telling. Now it's okay. Now it's fine. Okay, so as of now, people are telling it's fine. Okay, Philip is still it is blurred for you. I'll request you to please disconnect and connect once. I feel the problem is network is with your side in that case, if the other people can see. Okay, so at any time if it is coming blurred, no, because I'm assuming that the screen is visible to you and I'm just keep on explaining the code. If it is not visible, please let me know. Okay, I'll just zoom or something I'll try to do. Okay, so now okay, so now yes, so I'm printing the data set. So if you see here, the data set is in the form of a dictionary, which is nothing but a key value pair. So how it is coming, actually why I was zooming out so that you can see the entire thing. Okay, I'll try to show you in this way. So I'll show you. Okay, I'll highlight and try to show you. So first of all, you have something with the key as data. I'm highlighting it here. Okay, so you have a data. In the data, you are having all the values of all the features. Okay, followed by, so can you see there is a key value pair where the key is data. This much you understand. There is a key value pair which is with the key as data. There is one more key value pair with the name as target. I hope all of you understand what is this target variable. This target is nothing but a series of zeros and one, where the 0 is going to be my benign or 1 is going to be my malignant or the vice versa, something like that. Yes, so this is my target variable, which one I want to predict. And the last one you have as so last we have something as my features. 1 second, where it is gone. Yes, and the last one is with target names, which is an array, which is this is my, for the target names is an array of your malignant and benign. Okay, so 0 is for malignant and 1 is for benign in that case. And here, let me go to the right side. You can scroll, you can execute this code and see it is how it is showing. The entire thing is getting printed. And the last one is a feature names. The last one is a feature names, and feature names is another array which has a name of all the features, mean radius, the mean texture, the same data you have seen now, mean radius, mean texture, mean perimeter, mean area, and followed by all the others. Let me go zoom it here. So all of you can just scroll, play a little bit with your screen. I'm just trying to show you my screen as much as possible. So remember this entire data set here, the way it is getting loaded from the sklearn data set, it is coming in the form of a dictionary where among all the fields I'm getting, the three things will be of my interest. One is the data, the field with the data key, which is having the actual data. Okay, I mean all the values. Another thing I'll be interested in my target. Okay, that is going to be target array, which is going to be either 1 or 0 or whatever it is, depending on benign or malignant. And followed by, I have one more, that is my feature. I just now have shown you. I'll just go it again a little bit down, scroll here. Again, see it here. All of you just please do this step with me. I'll request you. So you will see it here down. One second, it's not getting scrolled. I think you can see there was one more with the feature selection, correct? Features. So this is the data set. If you print, it will show you. Okay. So now, so data is in form of a dictionary. It is not in the form of a data frame as such. Correct? It is not in the form of data frame or tabular format, how we have seen in our previous cases. So now you have to have a data frame format so that you can execute it. It's in a dictionary format. So what you should do? So you should do now the data pre-processing. How you are supposed to do it? First of all, what I have to load? I have to create a pandas data frame with pd.data frame. And which is the thing I have to load first? I have to load the data. What is this data? Breast cancer data set dot data. As I have shown you, the first thing that I have to load it here, interested, is this field, correct? This is the data, and the data set name is breast cancer data. So if you want to load the actual data values, all the data matrix, you have to write breast cancer data set dot data. So it will go to this particular key and load all the values belonging to this particular key. Okay, so this is what I want to load. So initially I am loading only the data. I'm not loading the target, because if I have to load the target, then I have to write breast cancer data dot target. So as of now, I have not loading the data. You can't load multiple things in one shot. So we are loading it one by one. So initially I am loading the data. Okay, so breast cancer data set dot data. Okay, fine. And I'm telling that from, yeah. So now what we are supposed to do? Yeah. So this is one time it is done, followed by which one extra we need? That is another one is my feature names, and again we'll be taking the target as well. As of now, we are mentioning the columns should be named with the breast cancer data dot feature. The last key, if you have seen, okay, the first key was your data, another key was your feature names. Okay, so this will be actually your data, and the columns for this particular data set will be taken from this array, which is feature names. So let me see the execution and you should be able to understand. Let me print it with the head so that you get the first 5 rows. Oh, sorry, I did not execute this one. Yeah. So if you execute this one, what will happen? All the data will get loaded here, and the columns will be named according to the array feature selection. Yes, that's what we did. Features, or not feature selection, feature names. So here we are saying the columns should be named according to the feature names. That's what has happened, and data has loaded from the data dictionary key. I hope up to this is how we are loading the data, which we have got it from the sklearn library breast cancer data set. So as of now, also the data pre-processing is not over, because I have got the data, barebone data, with only the feature value, but there is no target value, correct? Target value is what I am going to be interested in, 0 and 1. So what we have to do, we have to append that particular column. So this column is what I am interested in, breast cancer data set dot target, breast cancer data set dot target. So what we have done, we have added one more column with it. So the data frame, whichever data frame I have, in the data frame as of now, what is the situation of my data frame? This is my data frame as of now. Okay, with all the columns are there without the target. Now what I want, if you see here down, let me just scroll it here and show you if there is any target or not. Yeah, let me scroll it in the right side. So there is no target. The last one you're getting as what's fractional dimension and all. Okay, there is no target column. Now I have to append the target column with it for the further processing. So we have said that. Let me add one more column called label and take the values from the target field. So let me execute it. And now let me print. You can either use head to print the first 5 rows, or you can use a tail to print the last 5 rows. Just let me execute it here. So this is showing me the output. So let me go to the scroll to the right side and see that whether we have any target or label column. Yes, now you can see we have a label column. So where it is of zeros and ones. Okay. So this is my label column we have got, whether it's a benign or it's a malignant one. Correct. So now my data frame is ready for further processing. Okay, so if you want to see what is the size of the data, we have the 569 rows with 31 columns. If you want to, you can use the info to check out how many columns I have. I'm not explaining this commands because info shape, everything is explained a lot of times. You have to check that what is the. Okay, so someone is telling what is the last column, ma'am. Okay, I'll come to the question. Let me just finish this discussion and I'll just I'll get back. So you can check it if there is any missing value or not. Followed by, for the statistical information, you can execute the describe command and see it whether there is a chance of outlier or not. Followed by, you can check it with the value count. And you can see that how many values you have of the benign and how many value you have the malignant. So right now you have the benign value, 357 benign values you have, and 212 malignant value you have. That is the situation. And you can use a group by command to check the mean. This are EDA steps, we have done it, and you can see it, the mean radius of the malignant tumor is more than the mean radius of the benign tumor. So these steps are done for everyone. So I request you to everyone to quickly, just 1 minute, just execute this step up to this, and followed by where we can do the actual training testing and see the result. Followed by, you have to go for the artificial neural network. I request everyone to please start and just execute the steps and see it if you understand or not. Followed by, we'll check it with the logistic regression, what is the value we are getting. Followed by, we'll start our discussion with the deep learning model, TensorFlow, Keras, and the artificial neural network. Let me know if you're stuck at some point. Okay, so let me go to the chat window. Okay, someone has said how it is going to last. Okay, you click on this screen and just right, well, you press the right key. Print error. Which one is giving you print error? Maybe you've forgotten some step. X as of now we have not used, no? X, I think I have not used X as of now. X will come here down. X though we have not used, if I'm not wrong. X though will come here, the separating, when we are trying to separate. So please don't go ahead with up to X. I have stopped here. The separating the features and the target, I have not gone up to that step. So is it done up to this quickly? Check it out. So here I'm mainly saying that when you have data and you don't have it as a CSV format, you have it in the dictionary format. how to format it and get a proper data frame. And once you have a data frame, how to start with the basic preprocessing. So, okay, so if it is done, so let me just in 5 minutes, we can finish this particular one. And I want to really go to the neural network. So now the file is self-explanatory because yesterday we did this one. So first for the machine learning one, what we have to do, you can, so Keshav has said, yes. Yes means what? I mean, is it done for you? Okay. Okay, fine, done. So yeah, so right now what we have to do, you have to just you have to remove the target column. So we are separating the target column and you are dropping that column. And so yeah, so other things I think you can do it on your own. So you can try to print it and just printing the X and Y, where X will be your data and Y is nothing but your target value. I mean, different 0 and 1. Yesterday we have done it. Then what we have to do, we have to divide it in the splitting the data in the training and testing, and check it for the shapes, what is the size of the training data and the testing data. And then you have to load the logistic regression model, and to use it you have to do a model.fit and check it out the accuracy. For that you have to use the accuracy score. These things I'm not explaining, guys. Yesterday we did it. So and right now just print the accuracy and check it what is the accuracy value it is giving. So with this simple logistic model also we are getting an accuracy of 94%. Okay, that is on the training data. Now let me check on the testing data what is accuracy it is giving me. And for the testing data, it is giving me the accuracy of 92%. So with the simple this logistic model for the breast cancer data set, for the new data, I can expect to classify it with a 92% of accuracy. And similarly, you can predict, you can take any new data value, any new CSV, any new comma separate value you can take and build a predictive system. And let me execute this one. 1 minute, let me scroll to the left hand side. So what it is showing for, yeah, so I think you can show it as 1. 1 means I think it is a 1 means the data set the breast cancer is benign. Okay, so I mean, yeah, so you can try opening the CSV file and copy the value from each and every cell and see whether you are getting it as a benign value or as a malignant value, and check it with the original file whether you are predicting it correctly or not. So this portion of the things is done for me. So yeah, so last 1 minute, please check it off with the breast cancer analysis. With here I'm finishing all the portion with the machine learning. Now I'll be going to the artificial network, followed by tomorrow we will do the image analysis. Okay, so as of now, whatever I have done, the data is there in a data format, I mean numerical format or in the categorical format. So if the data is not there as a data format, it's there as an image, how to analyze it, that those are the things tomorrow we are going to do. So as of now, whatever we have done up to the machine learning thing, now I'm going to start with the neural network. Everyone understood anything you want me to ask? Done for everyone to this? So please reply that, can I move to neural network? Done. Very good. So it's done. So no doubts, I hope. Is it understandable, clear enough for everyone? Okay. Ma'am, is the command itself do LR? What does it mean by do LR? No, command doesn't do left and right. I think left and LR means left and right. Command doesn't do. You have to click here, as I'm clicking here, and you can click your in your keyboard. You have to click the left or right. Oh, LR is logistic regression. Yeah, it's logistic regression model we have loaded no here. Command itself does it. So let me go up. So while we have built the model up, yeah, so we have loaded the logistic regression model here, logistic regression, and we have used that particular model to fit on the data X train and Y train. Anything else from anyone? Okay. So if it is done, I'm just closing this screen, and now let me start with neural network. So before I start off, let me ask, what is neural network? Because a lot of time I'm just explaining everything. So yesterday I remember someone told that to explain about neural network, how to classify with neural network, or deep learning libraries rather. So anyone wants to comment on what is a neural network, what is deep learning, anything? No, nothing. Okay, so if there is no input from your side, I'll just play a short video on neural network imitating how brain works. Great. It's a very much correct thing that how our brain works. Our brain doesn't have any input output as such. We see something and get a feedback, whether it's the correct one or the wrong one. And that is how we learn. That is how when a baby is born, how they learn the language. No one tells them how to learn, but they learn it automatically, correct, with the automatic feedback. So that is how our brain works, which is a very correct answer. Thanks. So network connected as neurons. Yeah, very good. Correct. Both the things are correct. So let me play a short video on neural network, and followed by I'll explain what is neural network, what is activation function, and followed by we will see that how we can use that particular neural network to classify this breast cancer data set and what is the accuracy we're going to get. Okay, fine. So let me play this video. So I'm just, yeah. So once let me go back. So I hope the volume is coming. If the audio is not coming, if let me know.
Ma'am, it's not audible, ma'am.
It's not coming.
No, ma'am, audio is not coming.
Okay, so 1 second. I'll do one thing. I'll just I'll stop sharing and again share. I'll play once again. Please let me know if it is audible. Okay.
Last summer, my family and I
Is it audible?
Yes, ma'am. Yes, ma'am.
visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output compares the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train, but time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play, first differentiating the face from the background and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune. So, here's a question for you. Which of the following statements does not hold true?
Okay, so with this basic introduction of neural network, let me go to the PPT and let me explain what is a neural network. And then we will see how, with respect to code, how we can use this neural network. So, yeah. So as you have seen in the video nicely, that the neural network is nothing but a layer of neurons, which has the different layers. So first one will be my input layers, and last one will be your input layer, and in between you will have a series of hidden layers. It is not that you need to have only one hidden layer or two hidden layer. There can be a lot of hidden layers also, depending on how much complex a scenario is, and there will be the connection between the input layer and the next layer. So all these connections will have the weight. So if you let me just explain with respect to this. So here, this is one neuron in the next layer, which will have the connection with all the previous input, and each and every input, the channel will have the corresponding weight. So whatever input it is getting, that will be multiplied with that particular weight, and here it is my weighted sum it comes, and this net, that is my net input, and here we'll have something called as an activation function. So whatever summation I'm going to get, if it is more than the value of activation function, then that particular neuron here will be activated. What do I mean by activated? If this neuron is getting activated because the value from the previous layer is more than the value of the activation function, this will get activated, and this layer will pass that particular value, whatever weighted average value it has got, that will come to the next layer. Okay, so that is how the value will get propagated between one layer to the next layer. If the value is lesser than the activation function, that threshold, not activation function, I should say, it will have a threshold. If the value is less than a particular threshold, that if the threshold depends on the which activation function we are using, so in that case, the value will not get passed to the next one. So that is how the value will get propagated to the one layer to the another layer. So that is called the forward propagation, and at the end there will be a back propagation also, that as you have seen in the video. So the back propagation is nothing but a feedback loop, so that this neural network can rectify itself. So it is not that the neural network will iterate the data only one time. because there is a back propagation is there. So the neural network will iterate the data set multiple times. In your code, you can mention that how many times you want it to iterate, and as many times it is iterating, you will see the accuracy is increasing. Okay, because it will take the feedback of the previous iteration and it will try to increase the accuracy. Yeah, that's what we have seen in the video. So in the first time it was not recognizing the circle properly. In the next time it could recognize, correct? So similarly here also, that every time it will iterate, you will see the accuracy is increasing for us, and then you will see that at one point of time the accuracy will stabilize. I mean, the accuracy will not increase more, it will stabilize. That time we know that there is no more iteration is required. We will see it with respect to code. I hope it will be clear when I'm just doing the same thing with respect to code. So I hope all of you understand there is an activation function will be there. So activation function, there can be many type of activation function. One is called ReLU activation function, another is the TANH, another is the sigmoid function. So you can use many activation function. Each and every activation function defines a threshold. So if the value of the weighted sum, which is coming from the previous neuron, is more than the threshold value, that particular neuron will be activated. Now the threshold value will depend on the activation function that you are using. Okay, so I hope with this basic introduction of neural network and the activation function, we are ready to go ahead and start doing our coding in Python. So by the way, guys, I'm not explaining too much on the theory side because the portion that is suggested to me, it's a hands-on. So I'm trying to do more with respect to the coding portion of how to code this concept in Python using the Google Colab with the medical data set. So anyone wants me to repeat any theory portion of this, please please message here in the chat section so that I can yeah. So yeah, so some person told you are not required, I can go ahead with the coding. I feel it's fine, go for code. Okay, so some person has suggested, okay, so let me go for code. So any other person has any other suggestion, anything, if you're a person, so feel free to interact. Okay, so otherwise it's difficult for me to understand what you want. Okay, so now, okay, so what you do, people, go to day 2. And in the day 2, you will get this link. I guess all of you have, or else I'll share it again if you don't have. If some person has joined recently, I'll share it again. Wait. Chat section. I'm just sharing the link again. If you by mistake you don't have the link, so go to that link and you go to day 2, and in the day 2 folder you will see one one file called breast cancer. This one, breast project 4, breast cancer classification with neural network, NN. Okay, please open that one. And I hope, as I have suggested, please don't edit anything there. Please copy it in your local Google Drive, local file, so that you can edit and keep it for you. Okay, please open this particular file, everyone. Okay, so some person has suggested it's done for them. Okay, so let me go ahead now. So now let me go here. Go down. Just give me 1 second. I'll try to reconnect again. Just give me 1 second. One second, there is some network issue. The sharing is not coming. Okay, let me try to share it again. Sorry for the interruption. I think the screen is visible again. Yes. Yeah. Okay. So what we are doing here, just the initial steps, all of you, I'd request to execute it quickly. So we are importing the dependencies. It's the same as, okay, by the way, it is taking some time to get it connected. So it is connected. Data pre-processing and all, it is same as just now, whatever we have done. So please, all of you, execute all the steps quickly along with me. It's the same data set from sklearn library and which is there in the dictionary format and all. Please execute up to the line code of where you are checking it with for the shape and all. Just execute the code and see it, because these are all the steps that we should do always. Okay, just execute the steps. That's it. No, I'm not explaining. I'll try to directly go to the NN, neural network portion. So as of now, we have got to check the group by mean also. Okay, so separating the training feature, everything is done. After this, it will be same until then, unless you start loading the model. So print X, print Y, then split it in the test and training data set with the 20:20 ratio and print the shape. So please finish it up to the section of splitting the data into training and testing data. After that, we will start again how to doing the feature scaling, and then followed by how to use a neural network model. So I'd request everyone to do up to the step of splitting the data into training and testing data. Please quickly execute this much and then we will start doing. Once it is done, up to this step, splitting the data into training and the testing data, please message here as done. One person has told it's done. I'll just wait for one more minute for others. Okay, fine. Radvika also told done. Thank you. Okay, so now let me start with NN. So for NN, for any other model also, yesterday we did it. For NN, it is very much necessary that you, before you apply your neural network model to have a good accuracy, you standardize the data. Standardize the data means you use the feature scaling. Correct? Yesterday we did it, right? Standard scaler and all. The same thing, you finish it off, load the standard scaler and use the standard scaler to do the fit transform on the training data, X training data, and use the same thing to transform the test data. That is my X train and X test. I hope you remember that the Y field, the prediction one, you do not need to do any kind of feature scaling on that, because or the standardization on that, because that has only a series of 0 and 1, so no need to change here. Just 1 minute repetition. Why we are doing this standard scalar function, so that all the value, all the data columns will come in the same data range. Okay. So otherwise, different columns, some column will have the data value between 10 to 100, another will have between 500 to 1000. So the column which has a higher range, they will have more dominance on the prediction. So to avoid that, we are using the standard scaling. Okay. Now, so once you are done with this, now here only we should start our new thing. So this is what we want. I want to build a very simple neural network which will have a series of input, of course, and only one hidden layer I want to put, followed by the output. Okay. Now So for doing this, what you have to do, you have to import the TensorFlow and Keras. Okay, you're supposed to import the TensorFlow and Keras. So what is TensorFlow and Keras? This TensorFlow and Keras, I think all of you have heard of this or used it also. These two are popular library, the deep learning library. So this TensorFlow is a barebone framework for doing the deep learning application. Keras is built on top of TensorFlow to make the TensorFlow very much user-friendly. So Keras provides a lot of user-friendly APIs functionalities, so which makes the TensorFlow to work with the TensorFlow, it makes it very easier to do. Okay, so we are going to use both the TensorFlow and the Keras, and this random set seed yesterday also we have used, and here we have given it as 3. So it is nothing like that you have to give it 3 only. This randomization seed, you can give it anything else also. It is given as 3 so that every time you get the same output as I am getting. Okay, if you want to make it 4 or 5, that's fine, no problem. You can seed it with anything else also. So now let me import it. So we are importing the TensorFlow and the Keras, the required library for doing the neural network applications. So once it is done, now, so the required things are done. Now we have to set up our neural network, correct? Now how we want to set up our neural network, as I have said, I want to have only 3 layers. One is the input layer, another is the output layer, of course, and in the output layer we'll have always how many nodes? Output layer will have only 2 nodes, one for the benign case, another for the malignant case, correct? So this much should be clear, how many nodes should be there in the output level. Output level will have only 2 nodes, correct? Because there are only 2 levels in the output. 2 different classes are there. If there are more than 2 classes, then that many number of nodes should be there. Right now I have 2 classes, benign and malignant, so output layer will have 2 nodes. Now only one hidden layer. How many input nodes should be there? Remember, when you are supplying the data to the input layer, you can't give it as a matrix. So right now you have a data frame, correct? That's what you have. If you have seen the output of the head with the head command or the tail command, you have a matrix, 2D matrix with all the values of all the features. So but when you want to fit it to the neural network, you can't give a 2D matrix. What you have to do, you have to one feature, you have to give it as a 1D array. I mean, so if you have totally 30 feature, so if I go up, how many rows? Let me see that what is the size for me. Yeah, so right now X train has totally 30 columns, correct? So if you see here, the X train has 30 columns. So in the 30 columns means 30 features are there. So in that case, 30 feature should have been, I have to give it individually as one array. How many arrays I have to fit in? 30 arrays. So 30 array where one array will go, or one array or one feature data should be given to one input node. Okay, I'm repeating, one feature data should be supplied to one node. So in that case, how many node I'm going to need 30 nodes. Okay, so this much should be clear to you how we are building the neural network. You have to see that how many features you have, that many number of input nodes should be there. Okay, and output node depending on how many levels are there in the output. Okay, so now see it that how we are creating this neural network. For building the neural network, we are loading the neural network with the code called keras.sequential, which will load the NN for me. Now how to set up the NN? I have to make sure that I have to supply that how many input node, how many hidden number of nodes, how many hidden layer of nodes, and how many output nodes are there. So that's what is initialized here. If you see here, first one is my input layer. That is my keras.layers dot flatten. Why I am doing the flatten? Because I told that I can't give it as a 2D matrices, correct? You have to give 1D array. So that is why we are flattening the 2D structure as a sequence of 1D arrays. Okay, that is why the flattened word is coming. Okay, it's not a 2D matrix anymore. It's a flattened one-dimensional array. So, and the input shape equal to 30. Input shape is 30. Why 30? Because there is 30 features. Correct. So that is why we are using the 30 input nodes. This line, I hope it is clear, correct? So there's a flattened 1D array, series of 1D array and 30 input nodes. What about the last one, keras.layers.dense? By the way, I'll say you why it is dense. I'll explain. This is followed by, this is for your output layer. How many nodes we need in the output layer? It is 2. It is strictly 2 because right now there are only 2 levels in the output. Correct. And this in between, this is for your hidden layer. Here we have used 20. So you can play around with it a bit and try to check out that what happens if I, instead of 20 nodes, if I use 15 nodes, or if I go ahead with the 25 nodes. You can play around with it. So by the way, why it is dense and why it is flattened? Flattened, so I have explained. And if it is dense, it means that this layer will have the input from the previous layer. Okay, if you write keras.layers.dense, means this is not the first layer, it is receiving the input from the previous layer. Okay, now so for all these layers, as I have explained in the theory portion in the slide, you need to define what is my activation function. Yes, so that you know that what is my threshold, and if the value is more than that threshold, then in that case only that node will be, or that neuron will be activated and the value will be propagated to the next layer. So for every layer you have to mention the activation function. Okay, and I've shown you the graph that we have the different activation function that you have. ReLU is there, where the ReLU is quite popular, where the ReLU full form is rectified linear unit. That is ReLU. Okay, so what we have done here for the second layer, we have used activation function as ReLU, and for the third layer, we have used activation function as sigmoid. If there is no restriction, you can use anything, any other things also. You can play around with it, use tanh and see that what it happens. Okay, so now just execute it. See that whether it is getting executed or not. So here we are just setting up the neural network. We have not compiled it as such. So I'll request everyone to do up to this stage. So as of now, we have not calculated the accuracy, nothing we have done. We have not done anything with respect to our data. We just have created a neural network. We have just done the environment setup. So everyone please do up to this state and check whether you're getting a green symbol. It means that your environment, your keras neural network model is ready. Now you have to link it with your data set, and you have to check the accuracy and all this stuff. Please check up to this. Or any doubts you have, I'd request to please ask me. I'm waiting for everyone. Please finish it off, and after you are done and understood the things, and then you can message me as done. Or else if something, because we're starting with a new thing, neural network, if something is not clear, you let me know. So here we are just to do the step up to the setting up the layers of neural network. Please let me know if I'm going very fast. Yes, that is correct. To clarify, 30 input features. Yes, 30 input features are there. That is why we have given 30 nodes in the input layer. Okay, because one feature data will be going to one node. 2 in the output layer, because there are 2 levels are there in the output. What are the 2 levels here we have? We have the 2 levels as benign or malignant, which is encoded as 0 and 1. Okay, malignant, benign. and 20 is there in the in between hidden layer. There are different formulas for this. As of now, 20 is selected randomly, sir. But there are different ways to actually come out with what is our optimized value. Please Google search on this, that why this is 20. You can have different also. So up to this, it is done for one person. I'll wait for the others. Okay, 2 people have told. Okay, so let me start now. Now, so once we have the neural network model ready for us, what we have to do, we have to compile the neural network. What do I mean by compiling the neural network? You have to mention that how you are going to measure the performance of the model. The performance of the model, mainly we measure it with metrics accuracy. I hope all of you know what is accuracy metrics, because in the previous machine learning models also we have used this accuracy metrics after every training and prediction. We have used the statutory accuracy metrics. So same thing, the accuracy we're going to use, followed by there is an optimizer function and the loss function. So these 2 parameters I am not explaining because there are, I mean, what should I say? There is too many theory portions, and in that case, I have to execute. Remember, this is a optimization is Adam here, and the sparse calculated cross entropy. These are the one of the most popular values here for neural network. But there are many more variations also you can do. Okay, but for a simpler things, you can keep the loss function as sparse categorical cross entropy. I think cross entropy, all of you know this loss. I mean, the loss in the data set, this entropy, I think all of you know, if you are having the basic some idea about the decision tree and all, what is a loss function, I guess all of us we know. So remember this in a simple term, if I have to say without going into too much in the theory portion, that's what I asked. Anyone wants me to move to the neural network theory portion, please let me know. I can show that also, but as of now I'm just doing the hands-on. If anyone wants the details, let me know. Okay, so so for any model, if you check out the performance, you should go ahead with a model which is having the higher accuracy but lower loss function. Okay, I'm repeating, for any model, if you see the higher accuracy and the lower loss, that's better. Okay, so as of now I have created the model. Okay, this model is ready for us. My neural network model is ready for us. Now that neural network model has to be trained with our data. Okay, so where we have the data, let me scroll up. So we have the data after I have done the standard scaling. This is my scale data. So this is my train data standard, and so this is what will be used for the loading. So I'll have the data as X train standard and Y train. Correct. So this is should be my input data. So how we are going to use it? Let me go down. Yeah, now this is a step where you are supposed to train the neural network. By the way, I have not executed this step. Let me execute it. So let me compile the neural network. It's done. Now you have to train the neural network. So what you, by the way, there is a spelling mistake. Yeah, so model.fit. This thing you all of you have seen a lot of everywhere. It is a model.fit. Now with model.fit, what are the parameters? X train standard, that is my feature data, and for those, what should be my corresponding Y train, what is the corresponding value? This much I think all of you we understand. Then I have given as a validation split as 0.1. In the previous cases, we have kept it as 0.2, where 20% was the testing data and the 80% was the training data. There is nothing specific. You can keep it here also 0.2, doesn't matter. Okay, this one will say that how much should go for your training and how much should go for your testing. Okay, I mean, sorry, it is not that one. Sorry, extremely sorry, just mistake. This is a validation split because it will have the back propagation as well, correct? We said that will be having a back propagation also. So for that validation, how much data will be used for the cross validation? Okay, so that portion is your 0.1. Okay. Only the training data only we're feeding here. Testing data is kept as 20%. I'll go up again. Extremely sorry. Just we have somewhere here. Yeah. So here also the same thing. The training data is my 80% and the testing data is 2%. So in the training data, we are feeding to the neural network, and in that training data only for the cross validation and for having the backwards loop, the feedback loop, the validation split is kept as 10%. Okay. Now, what is this epochs? Epochs is equal to 10. You can keep it any other value also. So as of now, epochs equal to 10 means the model will go through the data set that many number of times. I'm repeating, epochs equal to 10 means this model, when I'm actually executing the model, if you have seen the video, it is not going to end with one iteration. It will, one iteration is over, then it will get the feedback from in the back propagation loop, correct? Then it will again iterate. So how it will change all the weighted values and all. If I'm just going here and I'll just try to explain if you understand this one. So this here, so let me just explain what actually do I mean by epochs. 1 minute. So what happens in the first iteration? Yeah, is epochs is similar to iteration? Correct. Yes, epochs is similar to iteration. So one iteration will happen and you will get the feedback that what is accuracy I'm going to get. That is with respect to your validation. Okay, the validation will happen and you will see that what is the accuracy I'm going to get. And that values will come back here in the back propagation. And how it will change, if you remember this, all these lines have some weight. Correct. All these connections have some weight. So now these weights will be changed here. In the next iteration, the weight will be changed here, and the neural network will again iterate the data with the modified weights, and it will try changing the accuracy. Okay, so how many ever epochs you give, that many number of iteration the neural network will do over the same data, with the different weights will get changed. In this lines of weighted average, correct? That's what we see. This is whatever x1 is coming input, that will be same. That is your data set, doesn't matter. Only what will change in different epochs, this weights will get changed. So that the weighted average sum is getting changed, and then this when you compare it with the threshold, you will see that whether that particular neuron is getting activated or not. You will try achieving the more and more accuracy. Okay, so epochs as of now we have just one second. So validation split, yeah, someone has told the validation split 0.1. I should explain. Yes, I'll explain. 1 second, let me go to the code. Yeah, so this validation split as of now, so this validation, what will happen? See, after every iteration, if you have seen in the video also, after, okay, let me go to the PPT only. See, one iteration is over. Okay, let me go to slideshow. I hope that's what I started with the video. If you remember that in the video, we started with a classification of different objects, correct? And we were trying to recognize that whether it is given a circle, it should say that it's a circle. And after first iteration, it did not correctly recognize it. So the accuracy was low. So what am I supposed to do? That feedback, I should give it here, correct, in a back propagation. And these weights will get changed. Now, how will you know that here the accuracy is low? How am I supposed to know? With the validation. So here, after the first epoch is done, whatever is the accuracy it is getting, how will you know what is accuracy? You have to validate it. Correct. So I hope you understand that there are two ways. See, once there is a big data set I have, I'm going to divide it manually in the training data set and the testing data set. And I'll create the model and with the training data set, and with after the training, I'll validate what is accuracy I'm going to get with the testing data set. That is different. But it is done within the training data set. This validation split is kept as 10% of the training data. So whatever training data you have, X test, in that 90% is being used to go and feed in the neural network. 10% data, we are keeping it to test it here. We are checking it, whether we are correctly predicting or not, whether that validation is proper or not. Okay, so this is the validation is kept for per epoch. Is it fine? Does it explain the validation split, what we are doing here? Okay, so this validation split will be done after every epoch. I mean, validation split is this validation, so that you get the feedback. Let me go to the coding now. Yeah, so this epoch is done. So now let me execute this one. Now it is, see here how it is coming. It is saying epoch 1 out of 10, 2 out of 10. So now epoch 10 out of 10 is done. It is done in 5 milliseconds, all those things it is showing you. And it is printing the accuracy also. So if you see in the first iteration, in the first epoch, it is showing you the the accuracy as 72% and the loss is as 57%. So initially I started with the accuracy value of 72%. Let me go and check it with the last accuracy value, that is at the 10th. And if you see here, it is right now my 96. So can you see every iteration, with every iteration or with every epoch, I have increased my accuracy. And if you see here data loss, I mean the loss in the correct value prediction, initially it was 57% loss. And now if I go down, it is my last level, it is my 13% loss. So can you see that you have increased a lot in with respect to the accuracy? Okay, so I request everyone to please finish up to this step and then we will predict it. And one question you may ask me, of course, that how will I know that it has to be the epoch is 10? Because epoch is very, very important, correct? Because with respect to that epoch only, we are getting the more and more accuracy. So what happens if it is not 10? Right now I have mentioned this epoch as yeah, so right now I have mentioned this epoch as 10. What if I mention this epoch as 20? So right now it is 96%. Will I be able to get 99% accuracy? May or may not be, right? So how to decide it? We will see it. I'll just explain that one with a graph. So before that, I request you to please go up to this and please check out whether you are getting the proper loss value and the accuracy value. Once it is done, you please message here as done. Yeah, so the same question, how to define the range of epoch? Give me 1 minute, I'll explain it right now. Yeah, range of epoch, I should not say it's a range. It is not a range. The epoch will start with always 1. I mean, the number of epoch minimum is always 1. There has to be 1 iteration, of course. The maximum value you should write. You should not mention 2 values. Only one thing you should mention, the maximum number of iteration. Does that depend on the accuracy rate? Yeah, yes, of course. But what I should say that it is not always that if you increase on the number of epoch and you will get the higher and higher accuracy. Then it's always very simple, right? That you make always give the epoch very high number and everyone will get 100% accuracy. It is not that simple because yeah, so it is not that simple because after one point of time when I plot it, you will see you won't increase much if you increase the number of epoch. Okay, let me do it here right now. 1 second. So for all of you, okay, so right now see the value. So right now I am epoch 10, correct? And you are seeing the value is 96%. Now let me re-execute this code. Okay, so let me make it as epoch equal to 20. Okay, fine. Let me execute it and see that from 96%, if I make the epoch equal to 20, what happens? It is executing. Okay, so for this one, actually it has increased. To be very frank, for this one, it has actually increased, but it maybe it is happening because, okay, there is one more issue. So I'll come to that. First, everyone, let me know that whether it is done or not. No, accuracy is not decreased, no, it is increased. Where accuracy is decreased? Accuracy is increased, no? No. Accuracy, why no? Accuracy is increased. So yeah, before it was 97. Now it is at the end, if you see here, Right now it is telling you 99%. But it is also not desirable. We will see it. So all of you have got up to this output. Can I explain that what can be the issue if we always keep on increasing epoch? There is a concept called overfitting. I don't have the picture of it. Maybe I'll just go in the Google slide and I'll just show you. Overfitting with respect to machine learning. Yeah, I'll just show in the Google image and I'll explain it. One second. Okay, let me just download this image. Just give me 1 second. Huh? Show it here. I'll explain the overfitting issue for you. Yeah, just let me explain this one. I hope my screen is visible to everyone. So remember what we are doing now. We have not touched anything in the testing data set, correct? You remember that whatever the entire data set was there, in that we had divided it in two parts, training and testing. And right now, whatever we are playing with it with the testing data set. And we have seen that I have just increased the number of epochs from 10 to 20. And yes, we have increased the accuracy. But is it always good? So now, so what actually happens, it's a general term, this overfitting is not with respect to only neural network, it is with respect to any machine learning model. So this topic is called overfitting. Let me write it here for your reference. 1 second. Let me write it here. Okay, this term is called overfitting. So what this overfitting term says, it says that you are building the model with the training data set, correct? So initially, if you in the x-axis we are plotting the number of iteration. Here you can understand it as the number of epochs, correct? So this is the number of iterations. So as you increase the number of iterations, here we are increasing the number of iteration. What is getting reduced? Getting reduced is my error. Can you see? As long I am increasing this number of iteration, my error will get reduced on the training data set. Correct? So remember, we have two kind of data set here. One is my training data set, another is my validation set or my unknown data set or testing data set. Correct? I hope all of you remember that. Initially, we have divided in two parts. 80% went for the training data set and 20% went for the testing data set. So we are, whatever model we have to build, we are building with the training data set. Correct? We are yet to test it on the testing data set. That testing data set is my unknown one. So now, as you have seen on the training data set, if we are increasing the number of iteration, yes, your error is reducing. Error reducing means yes, your accuracy is increasing. Correct? As we have validated it right now, from 10 to 20, your accuracy increased or your error decreased. But when the same model is applied to the validation data set, I mean the testing data set, whichever is the unknown data, what happens? This is called a sweet spot. When this model up to this level, on the testing data set also, your error will decrease or your model will become more accurate in prediction of the unknown values also. But after that, if you continuously go on iterating and try to optimize it on the training data set, you may try to overfit on the training data set, which may lead to the increased error in the validation set. I'm repeating, this issue is called overfitting because it may happen that here you have reached the accuracy of 96%, and here there is something, only one data point is there, and you are trying hard to accurately classify that one point, but that one point may be a mistake or some value which has come, a very weird value which will never come again. So if you try to optimize and get accurate result for that particular one point and try to modify the model with respect to that particular point, when that model is applicable, when you apply it on the general other data, it may not be able to predict correctly. So that's what it says, that this overfitting says that when you customize your model too much with respect to training data set, it may not perform properly for the testing data set or for the unknown data. Okay, so this is the issue which is called overfitting. So it says that after a certain point of step where we say that our accuracy is almost stable. Can you see initially the error is decreasing? It's a sharp decline. It's a sharp curve. Can you see? It's a quite sharp. It is declining. That error is declining. Now here, if I have to say, it's almost stable. Can you see? It is not changing too much. So in this region, if I go on and try to optimize, okay, what will happen when I apply the same model on the testing data set? Our error rate will go increase. So it says that never increase the what should I say? Never increase the epochs, so never increase the number of iteration up to after this sweet spot. After it is almost stable, after this curve is almost stable, don't go ahead and increase it again. Okay, I hope that explains. Now, how should I understand it is getting stabilized here? For that, you can predict and do the curve for it. So now, okay, so let me go back and make it 20 only, 10 only. So as of now, whatever we have done, we have decreased the accuracy. Sorry, increased the accuracy, but what we have done the overfitting, which is working nicely for the training data set, which may not work properly for the testing one. So let me go back to 10 only. Now let me see that the curves. What is a curve I'm interested in? I am interested to plot the accuracy, overall accuracy of the model and the validation accuracy, val accuracy or the validation accuracy. So let me plot it here. By the way, what is this history? If you see here, history is this one. History is here. This is a history. Okay, from the history we are plotting the validation accuracy. Okay, now see it here. It is not plotting. Some step I would not have done. 1 second. Why the curve is coming like this? There is something wrong here. It is not coming properly. It is not printing only properly. Just give me 1 second time. I just execute it again. You can also try doing along with me. The curve will not come like this. There is something wrong. Yeah, now it's correct. Yeah. So now if you see the accuracy, so okay, by the way, how we have plotted, let me just show you how we have plotted. So we are plotting the accuracy and the validation accuracy. So in this title of this graph, we have given it as model accuracy followed by the accuracy and epoch. So accuracy is plotted as a Y level, and the number of epochs, number of iteration is plotted as a X level. Now what is happening here? If you see here, in the training data also, if you see at the validation data, after this point, the training data accuracy is almost stable. At this point, the training data accuracy is almost stable. Can you see? So this is where I should say, this is what is my sweet spot. Here only we should stop, where the validation accuracy is also fine and my training data is almost stable. So if you see here, this curve is very sharp, correct? From here to here, the curve is very sharp. So so here also, actually you can continue up to 10 also. If you see here also it is coming, somewhere it is increasing. And if you see the values also here, let me go here and show you the values here. So initially the curve is very sharp. You see here, it is from 72 to 72. Initially it has 72, then it was 86, then it was 89. So it is jumping. So up to this level, it is jumping. See, up to 92, it is jumping. Followed by this, it is somewhere it is stabilizing. See, 93, 93, 94, 95. So it is almost stable here. Okay, so there is no point of going beyond 10 again. So in that case, it will become my overfitting case. Okay, so as of now, we have seen it, the validation accuracy and the model accuracy with respect to validation data and the training data. And we are seeing that it is almost fine. And similar way, you can predict the loss also, loss function, validation loss and the loss. And so if the accuracy is increasing, you can see the loss is decreasing. Yes, and after a particular point of time, you are seeing that these cars there is no sharp declination in the loss. It's almost stable here. Correct. So this is what is your epoch now. So as of now, we have done all the validation with respect to our training data. Whereas this validation data is a 10% of the training data. Correct. That is what we have done. If you remember, correct, while we have done this epoch, we have said this validation data should be where I have said, yeah, so validation split is equal to 10%. So validation data, we have kept it as a 10%, correct? So up to this, whatever we have played with the training data set only. That is my known data. Now we will see how this particular model will behave on the testing data. What is the testing data? Testing data is the 20% of the original data set. So I come to this, that how it actually performs on the testing data. Before that, I'll request everyone to do up to this step and see whether you are getting this graphs or not. Check it out, whether you can see it. And then next we will see that how you can build a prediction system and how you can check it with the testing system. And that should be done for the day. Now let me go ahead and go to the chat section. Yes, everyone, please check it up to this, whether you are getting the graphs properly. With the loss should be declining after a certain point of time, it should be almost a stable graph. And X does not have valid feature names. Okay, whoever is getting this errors, please start it from the beginning. Prabhavati madam has said it's done. Ajay said it's done. Plots are coming, but what is but? It is not correct. Initially, my plots were also not correct. Yeah, that's what my initially, or mine was also not correct. That's what I'm telling, madam, please, I think you can start again. Maybe what is happening, no, maybe while click execution, you would have not executed one step. Here, one step matters a lot because that particular step is the input for the next step. When I was executing it initially, I also did not get the proper graph, so I executed it again. Maybe I would have, by mistake, I would not have clicked on a particular execution. So normally this, please read. Whoever is not getting the plots like this, I request to do, because it should come like this only. Because all of us, we are using the same data set. The randomized seed is also set as 3. So whatever graph I'm getting, you should get exactly the same graph. We're using the online tool Collab, so there is no dependency on our particular system architecture. So all of us should get the same thing. Sorry. I think my sharing got stopped, right? 1 minute, I'll share it again. Yeah. 1 second. Grace, can you see my screen? It is sharing is getting, I don't know why it is getting. I didn't trying to share only, it is just getting disconnected. I hope now it's visible. Okay. I'll wait for 2 minutes more so that all of you are done with it. And then we will, if anyone is not getting, please restart, redo it. So tomorrow we will be using the PyTorch library, and we'll be doing the analysis with the image data. Okay, so today, up to today, I'm done with, as of now, for doing the data analysis with the, the data set form of a thing. Tomorrow we'll start with the image kind of data. That's what is my plan as of now. Okay, so let me just finish. It is almost time up. I don't want to delay too much. Okay, so this is whatever we have done, all this prediction and all with respect to my training data, which is my 80% of the original data set. Now I have to check it with the unknown data set, correct? That is my testing data, or the 20% of the data which I have kept. Where is that data? That data is there in the X standard, sorry, X test, correct? So I have, as of now, we have used X train to train the model. Now we have to use the X test to actually check the accuracy of the model that we have built. So what we are doing here, we are interested in two things. One is my loss and the accuracy, and we are evaluating the model. So for that, it is my model.evaluate. How to evaluate the model? I have to check for this model, what is my, what is the value that I'm going to, what is my predicted value, and what is the original Y test? Okay, what is the, what my model is predicting with X test data, what is the predicted value, and what is the original value. This Y test is the original value, correct? That will have a 0 and 1. That is a correct value for that particular data set. Now we have to check whatever this model is predicting for these features and whether that is matching with the Y test or not. The same step, I think we have done it for all the models. When we are done with got the model, we have tried to apply that particular model on the testing feature data set. We have seen what is my predicted output and match that predicted output with the original output. And we have tried to check out what is my accuracy loss and all those. So let me print it out. So if I print it, so it is showing me for the testing data set, I have quite a high accuracy. Its accuracy is around 97%. Yes. So if you want to print the other thing, so yeah, so other things are same as it is. We're just printing. The first one will be your output and all. It is just the size of the testing data set. It's nothing else. It is just the size of your testing data set. So your testing data set is a 20% of the original data. So it has the 114 rows with the each and one of has a it is just for your validation. And here you are trying to predict it. It's printed. It's just for your rechecking with a single value. Okay, it is just for your rechecking with the single value. So here it is coming. So just check it, then I'll explain here. Okay, so now let me explain at this point. Now this one I should explain. Give me 2 minutes time. Okay, so see it how you are getting the output. Remember one thing, let me go and show it in this output here, slideshow. For any data input, for all the machine learning kind of applications and all, what you got as an output, you got the output as 1 or 0. That is what we want, right? Ultimately, it should, whatever data I'm going to feed into it, it should tell me in the final layer, it should either got mapped to 1 or it should get mapped to 0. This much is clear for everyone, I hope, that whether it is a malignant one or it's a benign one, correct? But remember, this artificial ANN, this ANN network, it doesn't give that mapping. It will not give you directly 1 or 0. What you are going to get, you are going to get some probability here. Remember, whatever we are going to get here, we are going to get some probability here. Suppose this is 0.8 and this is say 0.5. Okay, and whichever is the higher probability among this, whichever value is higher, we are going to say that is my correct answer. So if it is 0.8 and if it is here as 0.5, I'm going to say that is what is my correct answer. I'm repeating this idea. This ANN in the previous models and all, it gave you directly 1 or 0, correct? And we are very happy with it. But ANN will not give you directly answer as 1 or 0. It will give you the probability for each one of the node in the output layer. Remember, this output layer may not have only 2 nodes. As of now, because it's a binary classification, there are only 2 levels in the output. So you have 2 nodes. There may be many more, correct? So for whatever nodes I have at the output layer, it will give me that many probabilities. And now whichever node has the highest probability value, that is my final classification result. Okay, so this one should be clear. So ultimate output is going to be my probability. Now from the, I have to see those probability and I have to check which one is my maximum and I have to say that is my answer. How to do that? Okay, so see it here. Yeah, so up to this we are done, right? Yeah, so now if you yes, let me print this one. So I have so yeah, okay. So what we are doing here we have taken only one testing data. Okay, we are taking only one testing. Let's see it. What we have done here to make you understandable. There is a question in the comment section. I'll answer that. Just give me some time. I'll just finish the discussion and come back to the comments. Okay. So what we have done here, first we are checking what is the size of the testing data set. So the size of the testing data set is 114. I mean, totally there are 114 data set. 114 rows are there in the testing data set. For your explanation, only one has been taken out. Okay. This is a first testing data row, first row in the testing data set. Okay. And what we have done, we have try to predict on that one. Okay, so I have just predicted on that one, this ypred. Let me execute this one and let me only print the first value. Okay, so this ypred 0 is a corresponding prediction of the x here. So this is the first row in the testing dataset. I'm repeating, this is the first row in the testing dataset. Totally the testing dataset has 114 row, correct? 114 row. When you are giving the final accuracy, you have to test it for all the 114 row and give the final accuracy. That's correct. But for your explanation, here it has been taken only the first row. Okay, I have taken only the first row and we have tried to check how this model will behave on the first row. Okay, so when that model is applied to the first row, I get my prediction. What is the prediction? This prediction is coming as 0.35. That is, I mean, the 35% or probability is 35%, and here the probability is 50%. Okay, so for if it is mapping to 0 and if it is mapping to 1, then I'm going to say which one is my answer. The answer is my 1, or it is going to be malignant or benign or whatever it is. I forgot that what was the one mapping. So right now I'm seeing this, the higher one is my 50%, this one. So I'll say this is the second node is my answer. So that's what was my point. See, for every data row, it will not give you answer as 1 or 0. You will get the answer as probability. Okay, and whichever probability is your higher or the highest, if there are many more probability values are there, that particular node is the answer. Okay, so right now the second one will be your answer. To do this in a simpler way, this is all the printing is done. You can just try doing the printing and check it. Okay. Okay, so to do this maximization, ultimately we don't want the answer as a probability, correct? You want ultimate the answer as 0 or 1 or whatever it is. For doing that, we have the function which is called the argmax. Okay, argmax function is there in the library function, which will check that whichever which one is higher and it will give that particular thing as an output. Okay, so just for the explanation of this one, this is what just a sample application. It has nothing to do with ANN. So right now we have taken a list. Okay, that's a normal Python list we have taken. There are two values. One is 25, 0.25, and there is 0.56. So this function is argmax function is given. It is available as in NumPy library, which is there as NP. NP is the short form of your NumPy library. So if you apply this NumPy library with the argmax function, what will you get? You will get the index of the max value. Let me execute this one. So can you see that once the input is this one, the output is my 1. 1 is my index, correct? So this is what is your higher index. Let me change it once. So let me change it as this message. Let me say it's 75%, and let me say it's as a 35%, and let me execute it. It should now show me 0. Yeah. So now you can see it is showing you the 0. So argmax function will return the index of the highest probability value, and this argmax function is available in the NumPy library. So if you want to execute this argmax function, you have to use it np.argmax. And where this is going to be useful, because we say that artificial neural network will give me the probability values for all the output nodes. I want to know which one is my highest one. Now, so that is connected. So converting, that's what, converting the prediction probability to the class levels. So right now, what we are going to do, because right now ypred, what is ypred? Ypred has all the probability values. Let me see what is ypred. Print ypred. Let me see print ypred. Can you see what is ypred? For each and every, how many rows are there? The rows will be there 114, because there is 114 testing data set are there. For every testing data set, it is telling you the probability. There's a probability of the first node, there's a probability of the second node, probability of the first node, probability of the second node for the second row. Okay, so if you want to check it out, you can print it ypred.shape also. Yeah, so can you see there are totally 114 rows, that is the same as your how many testing data set you had. Now let me change it. So just try to understand what it is going to predict. It is going to predict for each and every row two probability for the first output node, probability for the second output node. By looking at this two, you understand this is what should be the answer. Second one should be the answer, correct? But you can't do it manually. For doing it, we have the argmax function. So that is what is being applied here. Okay, it is iterating over all the rows in the ypred list, and it is printing the ultimate levels. Levels is nothing but 0 and 1. So let me execute this one. So now you are getting the list of 1 and 0s. Okay, that is your ultimate output, and this is your testing data set. And once you want to apply it for the prediction of a new data, right now it is a new input data, and that we have changed as a NumPy array, and followed by we have done the reshaping. So this step I'm not explaining because it's reshape functional. Everything I've explained yesterday. You have to reshape it, and then you have to do feature scaling, that is a scalar.transform, and followed by you have to apply that particular model to it. So we are applying this model here, and you are applying this argmax so that we know it is 0 or 1. If I click on this, it should show me the ultimate output as. Yeah, so it is showing me that as of now the values are 0.1 here and 0.8 here. So I know this probability is higher. So I know my one index is my higher index. So my tumor is benign one. So that is what is my ultimate output. So I think I have spoken a lot. It's already 3.56. That request, wherever you have left, please quickly finish it and ask me whatever doubts you have. So after the last discussion, let me just quickly cover it off, whatever we have discussed as of now. I just go up and let me just remove all the output. Okay, that will be easier for you. Clear all the outputs. Just for a quick recap what we have done. From here, I'll start explaining. First, we have loaded, quickly see it, we have loaded you can do it and listen to me also. We have loaded the two library, that is my TensorFlow and the Keras, followed by we have created the model with 30 input nodes, 20 hidden layer node, and 2 output node, followed by we have defined that what is my accuracy metric, what is my loss function and all, followed by we have tried to train our model with my training data set, and we have kept the validation split as 10%, and we have said the epochs is going to be 10, followed by we have plotted this plotting. I have this removed this plot. We have plotted the accuracy and the loss function, and followed by we have tried to check the accuracy of the model on the testing data, correct? And we said that when it is applied to any data row, it doesn't give me directly 1 or 0. It will give you the probability for all the output nodes, and whichever output node has the highest probability, that should be my answer. And how to get it manually, you can't get it by looking at all the things I have. For that we are using the function argmax, and this is what is the use of argmax. So guys, there's a lot I think I still told. Please execute it. Okay, down the questions. Please execute it. Take your time to execute. Another, I think, 3-4 minutes we have. 2 minutes we have. Very good. Okay, so does new message. Okay, just 1 minute. Let me execute one by one. Does input layer size decide execution time or number of iterations? Of course, it decides, and number of inputs also decide. Both, I should say. And this neural network, as you've seen in the video, there is no guarantee that when it will actually stop iterating if you do not actually mention the epoch. Anytime we do not we don't mention it as an epoch, we just say to answer accuracy is up to a certain level. See, whatever data set we are using it here, it's a sample data set which has less than 1,000 data rows. But when it comes to actual real life application, whichever you are seeing in the video, say the speech recognition and so many things are there. So it is going to be a very complicated data set with a lot of features, which is much more than 1,000, maybe the number of columns in that case. And in that case, and there will be a huge number of rows, maybe the 1,000 or lakhs. And when it starts optimizing on that, it's really quite complicated. As of now, whatever we are seeing it here, it's just a toy data set. Okay, so please execute it up to this if you understand the argmax function, if you understand the output format, because it's quite a little bit different, right? Because all the other machine learning model was directly giving you 1 or 0 or whatever is the result it was giving you, but it is just a little bit different. So Kusuma, there she has said that it's over. For the other people, I'll just still 1 minute. It's already 4 o'clock. I'll wait for 2 more minutes for everyone to finish, or if they have any doubt. Yeah, so if it is something like this, as we are using all the standard models or activation functions in case of research to develop a new model. Yeah, correct. So if see, as of now, whatever we are demonstrating it here, these are all the standard models, correct? But when you are doing a research on this, you have to change the parameters of this model. That's what I should say. See, here we know that what is a logistic regression model, and we are just applying it here and seeing the accuracy. Basically, whatever we are doing, it is just the application oriented, correct? Given it this application, how you are supposed to solve this application. But when you are doing a research, in that case, you are supposed to modify the model itself. Model itself means the parameters of the model, how the model is behaving, all the fine tuning you are supposed to do. Research means the model should be changed, not using the model. These are whatever we can show in the time limit of an FDP. It's the application of the models. But research or creating a new model completely, then you're supposed to check out whatever the variation of the model are there. See, if I take a model as a decision tree, there are hundreds of variation on the decision tree model, and each one of them is giving a different advantage. Okay, then we have to see that what is a research lag in that, and you have to come out with something else. See, if you're using the VGG 16, then see this deep learning model, in that case, it's very easy to do that. You are going to use that model and you will write one line code and it will give you the output, correct? So yes, it is. I should not say it is not possible. Yeah, so it depends on where you want to modify. Not sure did I answer your question or not, but once you are talking about research, you are supposed to modify the parameters of a particular thing. How the model is behaving, how the parameter is behaving, how the weighted average is taken, and all those model, how it is defined. As of now, whatever we are learning is how to use the model, how to interpret the model. Research means you're supposed to develop a new model, modify the model itself. Okay, so someone is asking input data as NumPy array reshape. One is for, because the reshaping is, I mean that you are telling it's now give me the NumPy array. Initially in the NumPy array we have loaded with it for the entire data set. It is now one because you are right now you're predicting it for only one row, correct? And the whatever models are okay. Okay, let me answer the last question. -1, you can keep it as it is. Okay, so what is I wanted to whether the few layers can be modified or not. If it is open source model, it can be modified, otherwise not. Anything from any other person? Okay, if there is no other doubt, I think I'd like to thank everyone for joining.
Thank you, ma'am. I think so. There are no more doubts. Thank you, ma'am. Thank you for this session, ma'am.
Okay, thanks.
Thank you, participants. So tomorrow, 10 a.m., the next session starts. You can all join at 10 a.m. Thank you.